I'd like to welcome you all to the Seattle University Projects Day. It's so nice to see members of the faculty, students here, family members, and of course, we appreciate our sponsors. My name is Professor Lisa Mlakowski. I'm a teaching professor in computer science. We have three wonderful teams presenting in this session. I would like to just ask for those of you who are attending virtually, if you have questions, to please put your questions in the chat, and then our moderator will ask your questions on your behalf. Other than that, I would like to thank our sponsors of this session, Boeing and Tacoma Truck. Did I say Tacoma Power? Sorry about that. We appreciate your sponsorship. With that, I'd like to introduce the first team, the non-motion detection team supported by Boeing.
All right, well, thank you, Professor. As you heard, we are CS2303. We are the Boeing non-motion detection team. So to start off, we're going to introduce ourselves. My name is Ethan Tarlov.
My name is Benedictus Albert.
My name is Hanson Aradi.
And I'm Hope Crozier.
And we'd like to thank our sponsors that we had for over the course of the entire year. So we had a lot of points of contact with Boeing. So we had Jeff Heiserman, Catherine Meza, Kevin Puterbog, Jim Troy, Rohan Rana, and we also had Chris Esposito helping us on behalf of Boeing. And again, I'd like to thank our advisor, Professor Lisa Mlakowski, for everything she's done with us the entire year.
All right, so I'm going to start us off with a little bit of context and background into the opportunity for this project. So our project has a lot to do with worker safety. Worker safety is something that companies are continually striving to improve and ensure to their workers. And lucky for us, we live in a world where technology has advanced to the point that we can incorporate it into our attempts to improve and ensure worker safety. Now, Boeing is a company that is interested in finding ways to monitor and ensure worker safety, specifically for their employees that are in isolated environments. Now, what is an isolated environment, you might ask? An isolated environment is just a confined space that a worker resides in that renders them unable to communicate to anybody else, so they can't really see or hear anybody else, and in return, nobody can see or hear them. So this specific environment was really the focal point of our project. Now, I'm going to go on a limb here and say that most people in this room are workers of some sort, so the term worker safety probably does apply to you. And while you yourself might be sitting here thinking, I wouldn't really benefit from an app like this, there's a good probability that you know somebody that would. So the goal of our project was to create a reliable safety system that would monitor and ensure the safety of workers in these isolated environments. And we did this by creating a mobile prototype application that we have called the Non-Motion Safety Detection app. So what does our app do? Our app is going to monitor workers for periods of non-movement when they are working. And in the case that a period of non-movement occurs for a certain amount of time, we're going to trigger an alert in the form of a notification that is going to be sent to personnel that are subscribed to this specific worker's notifications. Furthermore, we have also implemented a system that is going to detect falls, and we do this by monitoring both the orientation and acceleration of the phone and the corresponding user. And in the instance that a change in orientation is paired with a spike in acceleration, we're going to trigger a fall alert, again in the form of a notification sent to the corresponding personnel. All right, next we have a just general app overview of how our app works. So we're going to assume that the phone is on the worker, most likely in a pocket of some sort. And then in the case that an incident is detected, whether it be a non-motion incident or a fall incident, there's going to be a confirmation pop-up on that app screen. Now that confirmation pop-up is going to appear for a certain amount of time and gives the user the opportunity to confirm that they are in fact okay, they don't need any assistance, and it's going to deter any notifications from being sent. On the other hand, if this confirmation pop-up goes unresponded to, that is when that full alert is going to be triggered and the notifications are going to be sent.
Okay, so here are the tools and technology that we use for our project. So we chose Flutter as our main development platform. The main reason for choosing Flutter is because it is a cross-platform development system, and it uses Dart programming language as its main language. So it is super flexible. It can run on both Android and iOS without us having to run and maintain two code at the same time, one for the native iOS and one for the native Android language. And to run and test our code, we use emulated device on our computer. We utilize Xcode to run our iOS phone, and then we utilize Android Studio to emulate Android phone. And then there's also a notable feature from Flutter, which is called hot reload. So basically what this function is, every time you make changes on your code, in other language, you have to rerun and recompile your app, and it takes quite a while. With this function, with this feature, you can just press the reload button and it will reload your app immediately within seconds, and it saves us a lot of time. Okay, so for the non-motion and motion detection system, we utilize the combination of accelerometer and the gyroscope sensor of the phone. The accelerometer detects the acceleration of the phone, and we mainly use that for the fall motion alert system. And then for the gyroscope, it detects the angular motion of the phone, which we mainly use for the non-motion detection system. Okay, so our app is also supported by a Firebase server. So what is Firebase? Firebase is a set of backend computing system, and it is also an application development platform that is provided by Google. We utilize some of the useful services from Firebase. The first one is a Firebase authentication that we use for user identification, so we would know to identify who sends this message and who needs help and that kind of stuff. The second one is Firebase code messaging that we use to send and receive notifications within the phones. And then lastly, we have Firestore code database that we use to store the data of the users.
Now for the build of our app, there are two main user stories that our team uses. The first one is that as a manager, I want to be notified if a worker has not been moving or possibly incapacitated in a certain location so that I can send help to that location as soon as possible. And our second user story is that as a worker, I want to be able to send alerts to my manager in the event of possible incapacitation, indicating my current location so that I can receive help as soon as possible. Now our team works in over 16 sprints in the course of the 9-month project. Our project was divided into 3 phases: project planning, which we use 4 sprints for that, and then project development and testing, which we use 9 sprints for that, and our last 3 sprints are dedicated to project documentation and deployment. So some of our major milestones include we successfully delivered a complete set of features in our non-motion safety app. We also finished unit, widget, and real-time integration testing for each of our features. And we also provided documentation on each of our features, testing results, and created a user manual for end users to use. One of our major technology blockers that we encountered was that in the middle of March, we went on a factory tour to Boeing Everett facility. And there we realized that using GPS to detect the workers' risk zone of interest is not viable because one of our sponsors actually tried using the GPS tracking device inside the facility. And as you can see on the right there, it is highly inconsistent in the way that we don't even move close to 2 miles, but the GPS tracking device tracked that it is close to 8 miles, which is highly inconsistent. This could lead to future problems for our app to detect risk zone of interest using GPS. Thus, how our team resolved the issue, within the remaining 2 months time frame, we need to find an alternative, and our team decided to use the QR code implementation. We created 2 new features in our app. The first was that for the worker to scan a predefined QR code defined by Boeing with the risk zone location name and the risk level. And the risk level is to be used in a way that the higher risk level will be appropriate to the timer threshold that will be used for the period of non-motion. And the other feature is generating the QR code with the defined location name and the risk level.
All right, so we actually have some videos to demonstrate how the notifications would go off on our app. Due to some of the situations where it would require like a fall, for example, we only have videos for them. We will not be demoing them live. But to start off, we have Albert here turning on the phone and putting it in his pocket and beginning to work on fixing the table. And then all of a sudden, a high velocity object hits him out of nowhere, knocking him unconscious. Dangerous situation, and now he's no longer responsive. But because of our app, we notice that there's no non-motion, there's no motion, and it will trigger that pop-up, which is the confirmation to make sure that you're actually okay and that you're actually conscious. If you get no response, it will then send a notification, as you can see on the right side of the screen.
All right, next we have a video demonstration of our app in use for a fall alert. So this video here is going to show Hanson. He is going into the app and turning the fall sensing capabilities on. So now the app is going to be checking for a fall. And in this case, there is a fall. So that phone senses that change in orientation paired with a spike in acceleration. And here we see this confirmation pop up. And in this case, Hanson is unresponsive and cannot confirm that he is okay. So once it reaches that 15-second threshold, it is going to trigger an alert in the form of a notification similar to the one that you see on the right side of the screen here, just stating who is indicated to have fallen and what area they are in.
All right, so we got one more. We got a couple more actually. So we don't only have notifications for automated senses. We also have one for a manual send, just in case that they are conscious. So we also have an emergency button. So to demonstrate, Hope here gets put in the most dangerous situation possible, getting stuck between the couch. So now, to call for help, she goes onto her to the safety app and presses the emergency button, presses the confirm button, and will send the notification, as you can see on the right side of the screen, to users that are subscribed to her notifications.
Next is an alert that we actually implemented in the last 2 weeks of our project. During our deployment phase, we realized that when the user incorrectly sends an alert, we have no way of indicating if they are fine right now. So in our profile page, you can see there's an all clear button there where you can click, and there's a pop-up confirmation. And if you click yes, it will send an all clear message to your manager to indicate that you're all fine now.
So we actually learned a lot of major lessons over the course of this project. One of them was that we had to be adaptive to scope changes and be ready to change our scope and be able to fit it within the time restraint of this project. So the main example of that would be from the GPS. We came into it thinking for about 6 months that that was what we were going to use. And then we went on to and saw a real life example of how it would be used in progress. And it just kind of blew up in our face that it wouldn't be a reliable source of information for that. So we had to quickly come up with a solution, which we did with the QR code in a very short amount of time, and also implement that within the 2-month period that we had left. The other one was that we had to focus on the MVP and building the main features before adding additional features and enhancing them. So this is just something that came along as we realized as we were working on it that sometimes while it is nice to make the button look nicer, for example, it's not necessary in comparison to the functionality of the whole app. So just being able to work on and focus on the viable product, the minimum viable product of this app, and getting everything else working was more important. The other one is communication is key. We've worked on group projects as CS majors before, but not one on this scale for such a long period of time, where we were not only working with 4 to 5 other members, but also working on one code base and changing all one code base at the same time. So it's just a very dynamic work environment and also very different from what we were expecting from what we were used to in the past. We also have a couple of things that if we had more time, this is what we would have had more, what we would have done in more time was available. One of them was adding more alert types. While we may not have exactly thought of more at this current moment, the all clear was actually one that we added pretty recently, like 2 weeks ago was when it was fully implemented into our app. So we still have a lot of situations where there could potentially be a future alert type where it would be better for that to be specified in the future. Another one is adding more sensors. We put this as out of scope at the very beginning, but this would actually work great with the sensors on a smartwatch, like the heart rate sensor. I think the newer ones also check like for oxygenation of the blood. Like those could also be very useful for checking for a user is unconscious or for non-motion periods, where we can use those as well to enhance and figure out if the user is in a non-motion state. The other one is adding GPS functionality for non-warehouse environments. So as you saw in the earlier slide, it's not reliable in indoor settings. It's too noisy. GPS in here, for example, would not be reliable for determining which room you're in. But for outdoors, it's more reliable in that sense. It's less noisy and there's less noise pollution out there for the GPS to not get as bad results, for example. So we can actually use those in situations where we're in a more primarily outdoor setting for safety. And we still have that code in the code base. It's not deleted. It's just not implemented into the main app. But we could still use that for future enhancements for outdoor situations as well, just not indoors. And we'd like to thank you for coming to our presentation for CS 2303. And we're happy to answer any questions that you have at this time. Thank you.
it's not on.
The red light has to be showing.
My question is on the emergency alert, does that also alert EMS automatically or not?
It only alerts a manager on site or anybody that's subscribed to the notification. So we actually have a page that's called a workers page where you can insert a UID as on the profile page. There's a UID to connect with the user to Firebase. That is how we ID who is sending the notification and how we're getting information from it. So it only alerts within the app itself at this time. It does not contact EMS or emergency services.
Okay, thanks.
I just had a question. Like, did you guys ever consider the scope of like, if someone, I guess, did you ever consider having your app send like a notification to their phone to like ping the actual worker in case they forget to like, if they are okay, but they just, for some reason, the non-motion was triggered, but they just forget to hit the confirm, or they forget to confirm that they are in fact okay?
We actually implemented when you see the pop-up notification alert to confirm that you're okay, there will be a vibration in the phone so that the user can know if there's a confirmation pop-up, they need to confirm that they're okay with.
I guess too, like, so the app needs to be on your phone at all times when you're working, or if the user just has like their phone in sleep mode, will they get like a pop-up, like a ping?
Currently,
Yeah.
with how notifications are set up, it requires the app to be on, but the motion sensors do detect non-motion when the app is in the background, and it handles notifications in the background. But we never fix the issue with being able to send in the background as well. The app needs to be open for that. But once you open the app, it will immediately give you that pop-up of that you've not been moving for too long. So it'll trigger the actual action of in the process of sending it when you open it.
I see. Okay, thank you.
For me, it was actually working in a team environment with Scrum and Agile methodology. This was the first time for me, and I think it was the first time for all of us too. So, working in team projects wasn't something that was new to me, but it was more of just working with one code base, one version control in GitHub, for example, just working on one code base where we were all editing the same thing and just having to know when someone was pushing something onto GitHub and when I needed to pull or when I needed to stop working to tell my team that this is what I'm doing, I need something else done before. Just a lot of communication. And I think that this, for a learning experience for me, it was just communication skills for how to communicate with my team properly on when I needed things done and when I could get things ready for them to start working on other processes as well.
So my question is that I believe that your application requires a internet connection. So I'm guessing that what happened if the phone loses connection and or what if destroyed in a dangerous environment?
So the phone itself, for the main functionality of it, the only internet connection required is for the notification to be sent and received. In that case, it could work either on Wi-Fi or on cellular data as well. But for the notification to be received, it requires an internet service because you are connecting to other devices. So that was always a requirement. And while that is something that we did put into consideration of what was the main issue. That's why GPS was also kind of a hassle to deal with too, was because it required a constant internet connection, which you might not always have in a factory environment, especially at Boeing, for example, or even any other situation where you're outdoors, for example, working on the freeway. It could be used in any situation like that. There's always a situation where there's probably not going to be best case where you're going to get internet, but you can at least assume that you're going to get a small amount. That's why we try to limit it to just only notifications being the only part that required internet access.
Does it track if like it loses connection? Like say, like the example when I say the phone is destroyed, like let's say there's an incident where you get knocked out, but the phone is also destroyed in the workplace. Will you be able to track if it loses connection like that or no?
I do not think that we track anything to do with the hardware.
Currently, we don't have that feature, but that is something that was brought up once or twice. And so I think that is definitely something that could be somewhat easily implemented. Just checking, when was the last time we had connection to this worker? And if it's surpassed a certain amount of time, then, alerting a manager like, hey, this person has been without service for this long.
Thank you for all the great questions. It is time for us to move on to the next team.
And if anybody wants to see the app or anything, we have a running version of it at our poster table. So feel free to come check that out.
Good? Are we waiting for anything? Good? All right. Oh. Okay. All set? Alrighty. Hello, everyone. We are EC Team 23.2. This year, we are working for the Boeing company on the automated mobile inspection robot. I'm Jessica.
I'm Jaren.
I'm Y.
And I'm Coy.
So our faculty advisor for our project is Dr. Evan Moser, and our Boeing liaison engineers are the Dr. Jeff Heiserman, Alma Lemon Vici, Dr. Catherine Mazer, Rohit Rana, and Dr. Jim Troy.
So before we dive into our project, I want to first introduce you to our sponsor company, the Boeing company. So they was founded in our lovely city, Seattle, in 1916. They're mostly known for the commercial airplane. Some of the most common models are the 737, the 747, and the 767. The Boeing company also known for their defense, space, and security. Some example are they provide engineering solution, commercial derivatives. A prime example of that is how they modify and repurpose the 747 from a commercial airplane to the president aircraft, the Air Force One. They're also known for their global services like digital analysis, supply chain, and professional training.
So our project is about underside aircraft inspection, and there were three main areas that Boeing determined that could use improvement as of now. The first area is efficiency. Our solution would reduce the time between flights, as well as it would reduce the ground crew's workload. Due to our solution, the ground crew would also not need to be on site, which would increase their safety. And finally, our solution would provide a consistent and repeatable process, which would be a very useful tool for Boeing and the airlines they serve.
And the goal for our project is to build a mobile robotics platform with the integrated sensor and to develop a localization system that can determine the orientation and position of the robots. And robots have the ability to acquire the inspection data for distances and the inspection images, and to develop a testing process for our software and hardware.
So next we're going to talk about our research and the solution that we came up with. For the past year, we've trying to research and look for the solution for the problem. And some of the existing solution for this problem are ground-based mobile inspection robot, climbing inspection robot will climb on the actual plane to do the inspection, or the inspection using drones, which flies around. So after we carefully evaluate all the existing options, we decided to go with the ground-based mobile inspection robot because we think that it's best fit with our project scope, which is to scan the underside of the airplane. And also it fits with our test environment, which is mostly gonna be on campus. So we cannot have an actual robot climbing on our test plane and also having drones flying around in our room.
In this slide, we can see our final budget for our project. The most expensive item for this project are the RP lighter, motor controller, and robot kits. And the total cost for this project is $1,590.
So some background information about our project is that the prototype that we've built are just the proof of concept. So it doesn't mean to work on the actual tarmac and doesn't mean to work to scan on an actual airplane. Because of this, some of the allowance that we allow to have is that we will use a mock-up plane instead of an actual plane, which we will show to you later. Also, the testing run that we will do will be on an inside surface, so it's going to be dry and on a smooth terrain. A note is that all of our code for this robot is designed with Python, except for the graphical user interface, which is designed in C#.
So for our design solution, based off the issues that we talked about before, we decided to build a robot, a mechanism wheel robot that is, which has a flexible movement, which is needed for under aircraft inspection. And this robot is capable of taking images for inspection for the operator to view. And this robot is equipped with a LiDAR sensor, and this is for the localization process. And this is needed because the reception underneath the aircraft is not the best. So this will alleviate some of the location problems with the lack of reception. And this robot can also save and send data to the operator to view, and this is via the graphical user interface.
So this is the test plane that we built this year. Some things we had to consider when making it were the room size we had, as well as the materials we used and what they were capable of doing. The plane is made out of PVC pipe, cardboard, as well as some paper bags. It's about 10 feet long, and while Boeing has many planes in their fleet, we decided to focus on just 3-wheel landing gears, just to keep this aspect of the project as simple as possible.
So how do mechanism wheels work? So since we're using a mechanism wheel chassis, this will allow the robot to easily navigate in many directions. And this is because each motor has an independent powertrain, so we can individually control each motor's speed and direction. And as you can see in the picture on the right, if we move all the wheels forward, the whole robot will move forward. And if we move the top left and bottom right forward, and the bottom left and top right in reverse, the whole robot will go to the right. And here's a video demonstration of the mechanism wheels moving. And as you can see in the video, the robot has the ability to move left, right, forward, and in a rotational manner.
For our project, we have decided to use the RP LiDAR A2M12. RP LiDAR is a light detecting the ranging sensor. And RP LiDAR is a 2D 360-degree scanner. When we do the scanning, it gives us a distant angle. And from there, we have to convert them to X and Y in order to use them in localization algorithm.
So about localization, this is a very important aspect of our project. So localization is the process of the robot determining its position of itself with respect to the airplane that we are scanning. So as you can see on the picture right here, G1, G2, and G3 are the aircraft landing gear known position with respect to the nose of the plane, which is where the robot is gonna start its inspection path. D1, 2, and D2, 3 are the known distances between the free landing gear, and R1 and R2 are the measured distances from the robot to the landing gear, which will be measured by the RP LiDAR, which was talked about earlier. and theta is the angle between R1 and R2. So from these measurements, we will be able to find a robot at an unknown position. So go more into that. For localization to work, we need to have an algorithm which involves a lot of math. So we're just gonna simplify it by saying that the algorithm will include visualizing free circles that center around the landing gears and gonna be intersecting with the robot. Since they're gonna be free circle for the free landing gear, the intersection between the all free circle is gonna be the position of the robot that we are finding. The math about this, it's in the later part of the presentation if you guys want to know more.
One LiDAR does the scanning, it gives us the raw data in the picture. And our goal is to extract our 3 landing gears. And we have to do step by step. So first by filtering the noises and outliers. And after we filter the noises and outlier, we try to group the data points that are close together. From there, we try to go through each of the cluster data and extract our 3 landing gears.
The free landing gear is shown over there. Next, here is our robot. So the picture on the left are the top of the robot, which includes the 12-volt battery pack, which is the power source for the whole robot. So it's going to be connected to a circuit breaker, which also act as a switch, so we can turn it on and the robot on and off when we want it. Next to it is a power distribution panel. This component is going to distribute the power from the power source to all different components in our robot. Next to it is the DC to DC converter. This component just convert the 12-volt voltage level from the power source to the 5-volt voltage level that some of our components use. In the middle of the robot is the RP LiDAR. A note is that we have to make sure that the RP LiDAR has to be the highest component on our robot, so it doesn't accidentally scan other components on our robot. At the top of the robot over there is the camera that we use for detecting picture for inspection, and around is a LED ring light to help increase the image quality if needed. A picture on the right is the inside of the robot, where you can see in the middle right there is the Raspberry Pi, which is the brain of the robot, where all the data from the LiDAR and the cameras will be analyzed. And next to it are the 2 motor controllers. These will help us with controlling the speed of the motor in a closed loop mode to increase the position, the precise position of the robot.
So here's a video of the inspection process that we have created. So at the beginning, the robot is placed anywhere within a close range of the landing gear. And from here, it will be able to determine its position relative to the landing gear from the LiDAR. And it will move to the set starting position that we have decided. And from here, the robot will follow an inspection path that we have created. And on this path, it will capture images of the underside of the aircraft. And the LiDAR will scan for the position that the picture was taken so that it'll know where it is. And during this process, there will be 5 images taken in total. And this is at the first one's gonna be at the nose. And then there's one on the right wing, middle of the fuselage, the left wing. And finally, the last one is at the rear stabilizer. And after all 5 of these images are taken, they will be sent to the operator to view in the graphical user interface.
So once these photos are exported from the robot and they'll be imported into the GUI, we will take the photos and import them in. And then once we import the photos, they will all be placed on an outline of a plane. And this shows exactly where those photos were taken via the LiDAR data. And when you click on a photo, it shows you the photo that was taken recently and then a reference photo to the right. This reference photo was taken when the plane was in good condition, so the inspector who's using this application is able to determine what potential other things need further inspection.
So in conclusion, our robot is able to determine its position from the 3 known landmarks that we have. relative to the origin point. And this robot is capable of capturing images and embedding it with localization data that we got from the LiDAR. And finally, we have created a GUI that allows the user to inspect and view the images taken and compare them with the previous aircraft's condition.
So some things that we would improve if we had had more time in this project. As first, we would start with the GUI. Instead of doing two photos side by side, it could be better to flip between two photos so you can more obviously tell any differences between them. Next up, we would also implement a different background photo. As we take more photos and the scan becomes more complete, it would be helpful to have a more accurate image of where the photos were taken on the actual plane. Next up, we've made a lot of progress with our LiDAR, but there are still a couple parts of the algorithm that need to be tweaked so it doesn't pick up so many things that are far away and that are not landing gears. Finally, because we are a proof of concept model, we were allowed to test on a dry, indoor, smooth surface, but if this prototype ever wanted to make it any further, it would definitely need to endure some different surface testing. And finally, just due to time, we were not able to correct for the position before it takes the photo. But if this were to go any farther, future team would need to correct for position so the photos could be more consistent throughout the whole process. Thank you for listening. Does anyone have any questions?
Yeah, I just had a quick question about the physical design of your robot. So I noticed that you had the wheels, what looked like to be on the side of it. And what was the design thought process for that if you're considering that if you're moving that robot across a floor on the tarmac, if there are things that could possibly hurt the underside of your robot, what would it have been a possibility to have raised the bottom and just have the wheels kind of more geared towards there, and then that would thus allow the top portion to be even closer to where you're trying to scan?
Yeah, we did think about that possibility to raise the robot, but because we have limited of time, so we decided to build the robot by buying a robot kit, and the robot kit is already designed for us, so we cannot really modify that.
Makes sense. Thank you.
I noticed that every time the robot goes in a straight line and it's about to change direction, it stops for a few seconds and then continues on. Is it recalculating its position? Or do you kind of know generally what the distance should be and just keep going?
So in the video, it shows that it was following its predetermined path that we have. And every time it stops, it resets its encoder counts, so we can determine how far it goes to the next location.
What does the process look like for getting the images off of the robot and into your GUI?
The current process is at the end of the inspection, it gathers all the photos, and this wasn't mentioned, but the camera we use has a bit of an effect. So before it sends the photos anywhere, it has to calibrate based off photos we've already taken and basically do some image correction on the photos so they all can turn out and every line that is straight looks straight. And then after that, they get sent into, I have a Python script that just packs them all into and sends off an email right now. And that email will can be any email, and from there you can take it off your email and import it into the application.
Two small questions. The first one is just a small one. I know that probably is not the main focus of your project, but does the robot have the capability of detect obstacle when it move around under the airplanes to detect, to take pictures and to inspect their aircraft? That's the first one. And the second one is, where's some of the challenge that you have during your project in a stand-up approach, process and troubleshooting, and how do you overcome it at the teams?
Currently is not able to detect obstacles just for the sake of simplicity and making everything come together in a working manner for now. But it really is just a first generation prototype, so there's plenty of room for it to grow. As for challenges, I know one of our biggest challenges was getting the LiDAR sensor to work because the room that we were testing in has a lot of other things in the background that can cause noise that the LiDAR can sometimes sense as or the algorithm we use to filter out can sometimes sense as a landing gear when it's not.
Another challenges that I think about is that the robot, when it moves, it's kind of, because the mechanism wheel, the surface that we're testing on is on a carpet. So when it moves, it's kind of skidding a bit. So we have to like change it a lot to make the skidding like as like minimal as possible.
Please use the mic. It's for the online people. Oh, thank you.
So I know about Zero about robotics and stuff, but I was wondering, did you consider putting the LiDAR on a telescopic rod or anything to change the height for any measures or anything?
We just put like we make like a plastic thing for it. Yeah, we 3D printed like a plastic thing to make the height higher to make sure that the LiDAR did not hit any other components, but that's about it.
The LiDAR is also a 2D scanner, and so putting it higher or lower anywhere on the robot doesn't really affect how it scans or what it scans because it's still scanning for those 3 landmarks, and those 3 landmarks are going to be at the same spot vertically, regardless of where the LiDAR sits. And so we figured to have it closer to the robot so we're not having a big part up in the wind.
I see. So the inspection from under the craft is photo, and the LiDAR is only used for navigation, and it's not looking for defects.
Correct.
Thank you.
Thank you for all the questions. It is time for us to move on to the next team. Thank you.
All right, well, thank you all for coming today. We are ECE 23.5, and this is our capstone project presentation on commercial electric vehicle charging station design. I'm Manuel Aguirre, and my teammates are Brittany Giangara, Matthew Lee, and Cameron Ching. Our team leads are Jeremy Stewart and Riley Simpson on behalf of Tacoma Power, our sponsor, and our team advisor is Dr. Mehmet Verkach.
So our sponsor, Tacoma Power, they are a division of Tacoma Public Utility that was established in 1893. They provide power to about 162,000 customers, where 55% are inside their city limits and 45% are outside their city limits. They mainly generate their power through water dams. They also work with different clients for private projects, like changing overhead line to underground.
So we are under budget since the project is over. Since we plan to do 5 site visits, we only required 1 site visit. And we didn't need to pay for any excess mileage. And the project center is providing our liaisons parking passes. There also is no printing expenses since we didn't need to print anything.
So a little bit about our project motivations and goals. Tacoma Power is responding to some design requests at several sites throughout the city. for electric vehicle charging stations. And as such, they've asked us to research secondary systems that will help provide and manage power, specifically managing peak loads, which we'll talk about in a moment. So we are responsible for evaluating those technologies from an Excel standpoint and also performing some cost-benefit analysis on what implementing those technologies might look like, as well as submitting some high-level design drawings about possible configurations per each site.
So the solutions that we chose are all clean solutions. The reason being it was our liaison's request, and also we didn't want to provide any extra environmental damage that's already occurring. And the ones that we chose are batteries, hydrogen fuel cells, hydrogen electrolyzers, charge management software, and solar. So batteries are able to store and supply energy. They're similar to hydrogen fuel cells, except hydrogen fuel cells take water or take hydrogen and then hydrogen and oxygen and then combine them into water, and that reaction provides energy. Hydrogen electrolyzers take water and they separate it into hydrogen and oxygen, and that hydrogen can be used as a fuel for other devices. For charge management software, our main goal is to manage the load, which we'll be talking about in the next few slides. So that will help to distribute the load and not have very many peaks. And then we chose solar because it's another way to generate energy in a clean manner.
So in this presentation, we will be talking a lot about load shapes. So load shape, what it is a breakdown of the site load to the hour. So in this example, in the red is the DC-FC load, and in the black is the level 2 chargers. Together, you can see that there's a peak load around 5 hours.
We'll also be talking about peak loads and load balancing. And basically, peak loads are the max 1 hour demand a site will have in a year. And what's significant about that is that those peak loads determine kind of like the infrastructural commitment that the utility has to provide in order to accommodate that peak demand, as well as it kind of sets your demand charge, which is a scaling value that the utility will use to bill you. Additionally, unmanaged peak loads, they can damage electrical systems.
So right off the bat, we decided to not really look at the solar all that much. So initial analysis, as the example you can see here, the red line is the solar projection or the amount of energy that solar is making. And then we compared it to 10 residential level 2 chargers, which is like a basic electrical vehicle charger that you guys can see to like plug in any car that you would drive. So the solar array that we used for this example was like one of the biggest solar array that we can use for these kind of projects, was a 50 kilowatt solar array. So right off the bat, you can see that the red line and the black lines do not meet up, meaning that we would need to have a storage system like a battery, which is costing the project extra money. Also, as you can see on the left there, within 1 year, the solar array is projected to generate about 50,000 kilowatt hours. The sites that we looked at were using anywhere between 165 to 2.1 million kilowatt hours, so nowhere near close to the amount of energy that we need. And then the amount of energy, or the amount of money that it generates per year, as you can see in this little point right here, $4,500. The cost for the solar array that we used was $300,000, leaving a payback period of 66 years, which is extremely high. For this project, we did a lot of Excel modeling. So here's a little rundown of the example we did. So we took the site information that Tacoma Power was looking to design. So for this site, they're looking to install 200 level 2 chargers. Each site or each charger will be using 2,500 kilowatt hours per stall, as you can see by the second bullet point there. And then this point here, the load shape, this load shape was provided by Tacoma Power from a study that they did. So we took that information, put it on our Excel sheet, and then applied it with the load shape that they gave us. And at the bottom, you can see here, the site ended up having a peak of 591 kilowatts and total energy use of 500,000 kilowatt hours. So for the site, we had to design any solution. So for this site, we chose to do the battery. So we decided that the battery would output at 275 kilowatts per hour as long as the load was above this minimum of 150. And then it would charge the input at the top value, it would charge at a rate of 50 kilowatts per hour. So using that information, we were able to lower the peak down by almost 200 kilowatts. And the total energy used was pretty much the same. It's a little bit higher just because the battery's efficiency is about 90%, but overall, this actually came out to reducing the cost by a lot.
And the sites that we're going to be talking about are 2 public parking garages, 1 private parking garage, the Tacoma Police Headquarters and Fleet, the Tacoma Rail Yard, and a Trek parking lot.
Sites 1 and 2, we're going to be a little bit more brief on, just because their analysis is very similar to Site 5, which is a residential parking garage we did. But yeah, Sites 1 and 2, they are public parking garages, and they have pretty similar load shapes to the residential parking garage. One thing to note is that we discovered that batteries and hydrogen solutions were not cost effective. And that charge management software ended up kind of being the only cost-effective solution in these situations. But we've chosen to exclude the subscription cost because of kind of the variance in pricing for those. But yeah, that's for sites 1 and 2.
So the third site that we looked at was the Tacoma Police Headquarters. So for this site specifically, there are 2 buildings, the headquarter building itself and another building called the Fleet Building. So for this site, they're looking to install 22 level 2 chargers and 10 DC fast chargers. So the way we did this site was we took those chargers and split it in half. So 11 level 2 chargers and 5 DC fast chargers would go to one building, and the other set would go to the other building. Some little points that we needed to take a look at for this site was that Tacoma Police Headquarters building had a 1,000 kVA transformer, and it currently sees a peak of 309, meaning that we have about 700 kilowatts to work with for this site. And then for the Fleet building, there was a 700 kVA transformer, and the building's peak load was at 176, so we had about 500 to 600. And then another thing is that the Fleet building was looking to install 500 kilowatts of HVAC service. So for this building, we had to take into that account when sizing our transformers. So looking at the load shape after adding the chargers to the site, we can see that the site would see a peak load, or the building would see a peak load of 196. And then with the battery and the hydrogen fuel cells, which provide energy, we were able to lower the peaks by quite a bit. Hydrogen electrolyzers didn't lower the peak because the way hydrogen electrolyzers work, it doesn't provide energy. It uses extra energy, which is why the total energy went up by quite a bit. But it's using that energy to make hydrogen, which we could sell or use for another matter. Charge management software, as stated before, is used to slow down the charging rate so that it can lower the peak. The problem with this site was that, as you can see by the red lines there, which is the DC fast chargers, we can't use charge management software for DC fast chargers or any type of charger that needs to charge right away, because slowing down a fast charger kind of defeats the purpose of a fast charger. So here's the 10-year cost for these projects. As you can see, they're pretty expensive. Overall, almost every solution ended up being more expensive than just not installing anything. But for the purpose of the project, we chose the charge management software plus the battery solution for one, a proof of concept, and also just to test out to see how much of a difference it would make. And as Manny pointed out before, the charge management software cost is not being taken into account just because of the variance, so we're leaving it as a to be determined cost. And then here's the cost for the Fleet building. It's pretty much the same thing as the Tacoma Police Headquarters building. The only difference was that due to the HVAC or the AC services they're looking to install, we had to upgrade the transformer no matter what, because adding 500 when they only had 600 space left didn't leave a lot of room for anything else to be added. So we had to upgrade the transformer for every single one from the 750 kVA to the 1,000 kVA for every single one, which cost about $750,000.
So our next site is Tacoma Rail Yard. They're looking to install 10 level 2 chargers and 2 700 kilowatt locomotive chargers. Currently on the site, there's a 300 kVA transformer and a site peak load of 91 kilowatts. So for the load shape of the site is in the extremes. At a certain point of the day, it uses a lot of energy, and at other time of day, it doesn't use energy at all. From this, it requires a really big transformer. Currently on the site with this load shape, the peak load is 525, but by using a hydrogen fuel cell, we can reduce it to 150. But in return, we have to use a lot of hydrogen. And for this example, it's 18,000. For this site, we decided to go with hydrogen fuel cells and hydrogen electrolyzer, even though it's being one of the most expensive solutions, which is the 10 million, compared to the no solution, which is 7 million. The reason we decided to go with this solution is because for the site, Tacoma Rail is looking to install a hydrogen run locomotive. Because of this, we believe that the excess hydrogen made from the hydrogen electrolyzer could be useful.
Moving on to Site 5, this is a private parking garage. As mentioned before, it's very similar to Site 1 and 2, but we decided to focus on this one. Currently, we're planning to install 70 L2 EV chargers, and they currently have a 500 kVA transformer, and the current peak load without any solutions is 222 kilowatts. So this is the load shape without any of the solutions implemented. There's a peak of 210 that occurs for a few hours, once every 2 days. And with the solutions implemented, the peak does drop. Also mentioned before, for electrolyzers, because they're not producing any energy, the peak is going to be the same, but there's going to be 4,700 kilograms that can be produced. So we can make back money by selling those by selling the hydrogen. And the solution that we chose for this site is charge management software and batteries. This was the most cost effective. It also lowered the 10-year cost of the no solution case, which is really awesome. It also doesn't require any external or any extra transformer to be implemented onto the site, just the 250 kilowatt hour battery.
And so Site 6 is a truck lot owned by the Port of Tacoma, and the design requests are for 15 70 kilowatt induction charging stations, as well as one 900 kilowatt DCFC. Another thing to add is that all new service is going to be added to this site, so there's no existing electrical infrastructure. And charge management software doesn't work here due to DCFC needing to charge quickly. And so here's the site load shape. You can see that most of it comes from the 900 kilowatt DC fast charger, but occasionally toward the beginning of the 2-hour period, there are peaks from the 70 kilowatt induction charging stations. And so you can see here as well that the battery reduced the peak load of the site from 3,400 kilowatts to 1,600 kilowatts. And the hydrogen combination and the hydrogen battery combination also reduced the peak demand, but due to practical considerations with hydrogen, like taking space and transportation, battery made the most sense here. And so ultimately, in order to implement the battery, we'll need a 2,000 kVA transformer as well as a 4,000 kilowatt hour battery. And the 10-year cost comes in at about $14.5 million, which is appreciably lower than any of the other options.
So the main takeaway from this project is managing the peak load is very important. It helps to reduce infrastructure and energy cost, as well as not all solutions are going to be effective. For charge management software specifically, it can only be implemented when the load or when energy is not required immediately. So for the DC fast chargers, we weren't able to implement them, as well as the Tacoma rail yard, since the trains require the energy pretty quickly. So as mentioned before, it would defeat the purpose. And hydrogen and battery solutions are very expensive. Hopefully they are going to go down in the future. And we're projecting for a 10-year because that's about how long the technologies are going to cost. So if we were to extend the project, then we would have to take into account maintenance and possibly replacement costs as well. Thank you for listening to our presentation. Does anyone have any questions?
Excuse me, with charge management software, did the software allow the user to override the charge management software? So for example, if you pulled into the apartment storage or the public parking and you need to get your vehicle charged in the 3 or 4 hours that you were going to be there, but the charge management software said, no, we're going to restrict the charge, could the user manually override the charge management software or not?
That's a good question. I actually am not completely sure. I know that there are different charging algorithms that can kind of provide different results. I think that it would potentially be possible to allow for users of the station on an individual level to modify the charging algorithm, given that the software is on a per station basis. So it's not like there's one piece of software necessarily controlling every station, but that's something that maybe if somebody else picks up this project, they can look into in the future.
So for charge management software, there's kind of two ways of doing it in terms of slowing it down. So there's one where there's a first come, first serve basis. So like if I plug my car in first and say Matt plugs in afterwards, mine's gonna charge faster. There are options where it's like some people could pay extra because like for public ones, you pay based on how long you think you're to plug it in. You could pay a little bit extra to be like, hey, I want priority. That's kind of how some people can take over it. There's also some like presets that some people could, like some public companies can do to like set like, hey, no matter what, you won't be allowed to, or if you do choose to do so, you have to like have like a certain membership or whatever.
Because it would seem like a little bit like the toll lanes on the freeway, right? They raise the rates up to $10, but there's still people that are willing to pay that, so the toll rates, the toll lanes get all jammed up. So it seems like if you use charge management software to limit your feeder size, that you'd have to be fairly draconian about, keeping people from being able to override it. So.
I apologize if I missed this, but for your solutions that incorporate a battery, where's the battery getting its energy from? And then second part, did you consider, before excluding solar, did you consider the possibility of doing a combo solar battery CMS?
Where is it? So yeah, so for the batteries, so the way the batteries are getting charged is takes the same place where the electric vehicles charging stations are getting charged from, which is from the grid. So the way we lowered it was basically saying like, we're gonna have the charge or the batteries charge at a set rate. So like have it charge at only 40 kilowatts per hour rather than having it charge all like 400 of it within 1 hour, just so we can lower that peak value. And then for the second question, we did look into combining solar. We did, so for every single solar solution, we did it with the battery, and then also to do it with charge management software. The problem was that solar didn't really have a huge effect on lowering the cost of anything. Every single time we ran the solar as a solution, it increased the cost just because within the 10-year period, like regardless of all of that stuff, it took forever for it to actually make its own money back with how little energy it generated for the entire year with the size of the solar array that we were allowed to use for the project.
We may have time for just one more question.
So with the battery solutions, when you guys came up with price, did you see any difference in price as these systems scaled in size? Because I'm sure from a design standpoint,
So initially when we were looking at the pricing of everything, we were taking into account like different brands. We definitely looked at Tesla was one of them. We looked at other company called Bess or Bless, one of those two. So then they did have it scale based off of the size and stuff, but also we had to take into account like some of these batteries may only last a shorter period of time. So after talking with Tacoma Power, who also spoke with some of their clients, we set all batteries to have a set consistent charge of $1,000 per kilowatt hour. Because I'm sure there are batteries out there, like Tesla does definitely have batteries where it's like, if you only use like 100 kilowatt hour battery, it might be slightly cheaper than using like a 1,000 kilowatt hour battery, like per the kilowatt hour. But overall, we wanted to just keep it consistent for the base of the project.
Thank you.
Thank you.
Yes, so yeah. Thank you for being such a wonderful audience, and thank you, team, for your work. And a quick reminder that if you have questions for any of our teams from this session, please do visit them at the poster session, which begins at 4:15. Thank you. Right, welcome back, everybody. We have two presentations scheduled for this session. So the first team is sponsored by Sound Transit, and the next team by KiloWatts for Humanity. Some quick reminders before we begin. For our live audience here, if you have questions, please do raise your hand so I can pass the microphone to you. We need this so our online audience can hear your question as well. And for our online audience, if you have any questions, please type in your questions in the chat window and we'll get to them. All right, I'll hand it over to the team.
Okay, howdy everybody. Welcome to our presentation. We are Team ECE 23.4, the Sound Transit Sockeye, and we are here today to present an HVAC health and capacity monitoring system. Now a little introduction to the team. We consist of Lucas Efkovich, an electrical engineering major here, John Nguyen, a computer engineering major, Laura Olson, another computer engineering major, Ace Taniguchi, an electrical engineering major, and myself, Matthew Turner, a computer engineering major. And then a bit about our liaisons and faculty advisor. We are glad to have Dr. Abraham as our faculty advisor, and then Craig Dolala, Benjamin McNutt, and Drew Peters as our project liaisons from Sound Transit. Now a bit of background on Sound Transit itself. Sound Transit is a local public transit operator in the Seattle metropolitan area and is responsible mainly, you'll know them for the Link light rail system in Seattle and Tacoma. They are also responsible for the regional Sounder commuter heavy rail, the Sound Transit Express bus service, as well as the being responsible for running and managing the Orca card fare system, which is also used by other local transit operators, such as the local buses here in Seattle. A bit of background specific to our project is that we are mainly going to be working in the Tukwila light rail station, which was built in 2008, so a bit of an older system, one of the first stations built by Sound Transit, and they're still building stations, and up to even this year, they're still working on the Bellevue station, and the Northgate station just opened as well. And so these newer stations also have smarter systems than were possible in 2008. So our job with this project was to retrofit this older station to update that system to current smart standards. And now an introduction to our project. Our focus is on the HVAC system that serves the communications server room in the Tukwila light rail station. The goal of this project was to create a system that would monitor HVAC health, collect and display data on a web dashboard for Sound Transit engineers, to identify the health of the HVAC system based on that data. And we also had a stretch goal that involved researching, integrating our system with Sound Transit's internal work order system of work order generation. The motivation behind this project revolves around the fact that if this HVAC system failed, that could potentially lead to damage occurring to the servers themselves, which would interfere with Link light rail operation, as communications could potentially halter at the station and would impact Sound Transit Link light rail operation very much. The parameters that we're using to detect these malfunctions are the humidity, pressure, and temperature within the HVAC within the communications room itself, as well as the current drawn and noise generated by the HVAC system in the mechanical room.
So brief overview of our project budget. We did do an extra revision, so that contributed to increased costs in the project supplies section. But we found out that Azure services were covered mostly by Seattle University subscription. So we've only spent a little bit in that section, as well as domain name contributed to the rest of the computing and cloud storage area of our budget.
So going into the design of our system, what we implemented, it consists of two basic sections. On the left here, we have the hardware sensor nodes. These sit inside the station and collect data to be transmitted. On the right here, we have our cloud infrastructure. This consists of a cloud server that stores the data in a database and allows the user to access it via a website dashboard, and as well contains a machine learning algorithm to determine the health of the station, the systems. So moving on to how we implemented the hardware. Here we have a rendering of the PCB that's currently deployed at the station in the comms room. It has a number of sensors, temperature, humidity, pressure, all that. It's powered by a 12-volt wall adapter. It has a microprocessor and a cell modem to connect to the internet and the cloud server. Each node is identical, so we're able to deploy these anywhere. There's no modifications needed there, so the system is scalable. The PCB was designed in KiCad, and the firmware was written using the Arduino framework. So first, the lab testing. The first stage in development was to test the device in a lab environment. The way we did that is we left it powered on inside of a room, specifically someone's apartment, for several weeks. And the purpose of this test was to make sure that the device could operate on its own, because no one's going to be checking on this device, so it has to work. Throughout the test, we expected it to transmit data to the cloud server, even through interruptions. So we unplugged the power, we covered the antenna to make it lose cell service and lose power. And the aim was to have the device keep working for the entire test and be able to automatically recover. This test was successful, and it did so for the entire duration.
After concluding our lab testing period, we went ahead in early May and made a preliminary site visit and installation at the Tukwila International Boulevard Station. 2 boards, one for each space. One goes in the HVAC treated communications room to measure environmental parameters. The other was meant for the machinery space housing the air conditioner, and that would measure the current drawn by the air conditioner and the noise generated by the same. It didn't quite go to plan. The first board, while working perfectly in its test environment, did manage to gather environmental parameters, but was unable to connect with the cellular network inside that space. The other board meant for the machinery room, it was able to connect to the cell network, but we had no way of actually assessing current drawn without an electrician present. And that board was not equipped to be placed in the comms room. It didn't have the correct sensors for environmental parameters. So we made a second visit on May 30th with one board, which proved to be successful. That one currently sits inside the communications room, the treated space, and transmits our chosen environmental parameters to our server. So this current revision, the one sitting in the room, still has some outstanding issues. It's still inconsistent. Our second board, which is identical to that board, is as of yet unable to connect to the cell phone network. We still don't have a working microphone. So a third revision has been designed, but is not yet prototyped, a project for a later time. And for a complete picture, we really do want a second board inside the machinery space.
Now moving on to the software side of things, specifically revolving around the Azure server that we are using for this project. The first sort of thing that we have to deal with in terms of getting the data from the device to the server itself is message routing. So we used specifically the MQTT infrastructure to have a publisher running on the device itself, and then we have both a broker and subscriber running on an Azure virtual machine, which pulls data from a weather API as well as the current date and time, conglomerates all that data together with the data collected from the sensor, and pushes that all to our database. We do this specifically using the PAHO MQTT library for Python, as well as the OpenWeather API for pulling that outside weather data.
So the database is also hosted on Azure. It is designed using one table to ensure that all of the data has consistent collection times. So the columns in that table are outside temperature, outside humidity, outside pressure. Those are for the outdoor conditions at the station. And then the data from the sensors, which is inside temperature, inside humidity, inside pressure, and then current drawn, and 8 frequency buckets for an FFT of the noise sensor.
All right, in terms of the website, at the very top of the website, we have the status shown of the station. That shows whether the status is normal, cautionary, or in danger. Those thresholds are based on temperature given to us by our Sound Transit liaisons. Below that, we have the 2 boxes showing the temperature, humidity, and pressure of both the local area and the communication room itself. The local area is grabbed from a weather API that gives us the temperature, humidity, and pressure, and then the database gives us the information for the communication room. Right below that, we have the FFT, or the fast Fourier transform. It's showing the 8 frequency bins, and that's just an example on the board. And then below that, it's the current drawn over an hour and a half. And that's also an example. And the website uses is grayscaled per our liaison because we were asked to have a high performance HMI, and grayscale would fit that. And we have a endpoint given to us from Azure, as when we deployed the website, Azure gives us an endpoint to reach the website. And we also obtained a Google Domains endpoint as well, which can also attempt to connect to this website.
And then the last side in terms of, or last aspect of the software side of things is our machine learning algorithm that we actually use to process the data once it is collected in the database. So we've built an anomaly detection algorithm which is unsupervised, as we would not be able to consistently rely on somebody classifying all that data for us. So we have to rely on the machine learning algorithm to do that by itself. We are specifically using the Python library, the scikit Python library, which has an elliptic envelope function, which fits that elliptic envelope to the data set input, at which we then test that envelope against a set, against the test data set, and are able to test it in that way. We specifically use the Mahalanobis distance calculation to get all of the different variables into one specific column, and then use a z-score of that Mahalanobis distance to get all of that congealed into one z-score. So we are providing recommendations in terms of specializing the algorithm, as at this point there is no data collected at the site to specialize our algorithm to the site. But this general anomaly detection algorithm does work and will be able to be easily fit to the actual data once it is collected fairly easily. In terms of testing this algorithm, we trained using normally generated data, being 97% normal, 2% caution, and 1% danger values. And then we generated another set of using those same parameters, but only 1,000 of those. The accuracy on this preliminary test was 100%. Once we went back and did a bit more of an in-depth test, it remained at 98.6, so very, very promising for once we do have that data. And this machine learning algorithm, we are providing Sound Transit with the instructions on what a future team might be able to do in terms of specializing the algorithm. And what that mainly revolves around is feeding that data to this algorithm and then adjusting the z-score thresholds for the danger, cautionary, and normal values.
All right, so in terms of importance, this is fixing something Sound Transit needed in our older stations. It's a way for Sound Transit to monitor these stations remotely without having a maintenance worker come in and feel the temperature themselves or look at the thermostat, and that's time consuming. So this helps them with that. And also it's scalable. So this system is independent of any of the HVAC systems in their spaces. So we can plug and play this at any other station, any old station, and it'll essentially function the same way as it should for all of them. Questions?
Thank you. I think you mentioned unsupervised learning, is that right? And you also talked about accuracy.
Yes.
Do you want to explain?
Sure. Do you want to go over that? You did that more that second.
Yeah, so we don't have any real data. We were mainly testing that the algorithm would work on generated data, that it was something that would actually be useful. The accuracy for the preliminary tests is not indicative of what what we would get on the actual data necessarily, because we don't have any of that data. But we were just checking that it was working. And
like, since we are the ones that like generated the values, we know if it's a cautionary or dangerous value, so we can kind of test it like in that way. We don't let it know what it is, but yeah.
Thank you.
Questions?
Thank you. What kind of current sensor are you using?
It's a current clamp. So it's not currently installed because we couldn't get that board working, but the plan was to have a current clamp.
That makes sense. Another question, could you discuss a little more about connectivity in the communications rooms?
Yeah, so these communications rooms, they're inside of concrete walls, so the cell connectivity is somewhat limited. We had issues with some of the boards, a design flaw that caused inconsistent cell connectivity. So the one board that's in there connects just fine. However, the other board couldn't connect just fine. Not entirely sure. RF is kind of very complicated, so there was some issue. We believe we've addressed it in the third revision that we have not produced.
Did you consider having some kind of antenna outside the room?
That was not an option because we'd have to drill through the wall.
We have a Zoom question. What information does the FFT give the user or the machine learning algorithm?
So the FFT is specifically useful for determining if any specific range of frequencies is louder than it usually is. So if some louder, or if the higher frequency is louder than it normally should be, or is lower than it, or the lower frequencies are louder than they normally should be, as could happen in cases where the, for example, like a belt may have broken, or whatever it might be, if the HVAC system has broken and now sounds different, we are able to monitor that through the microphone, which we then take the FFT of I think a 10-second recording, and then using that we can just feed it into the machine learning algorithm, which will do the learning for us and the classification for us.
We have time for more questions, so keep them coming. Yes, Jim.
Part of your fitness program. So you're using cellular connection. Why wasn't Wi-Fi used? Are these sites not equipped with Wi-Fi?
We wanted something that involved their current systems as little as possible to avoid any kind of issues with network security and the like.
Are there any other connectivity choices that you guys have think of? Like, for example, LoRa?
Yeah, we did evaluate several, including LoRa. However, cellular was chosen because of its ubiquity. The cell network is everywhere, well, maybe except for the comm room, ironically. And we were most familiar with it.
So is there anything about transit that surprised you during this project?
I was surprised we needed a right-of-way pass to get onto a closed site that's nowhere near the trails, the track.
I was really excited because I really like public transit, and it was just kind of cool to kind of see what a comms room for a public transit organization looks like. And like, I just had never thought like, oh yeah, they do need to talk to each other. You can't just kind of run a train on a rail and hope that it gets there. So it was just kind of cool to see how that all kind of works. And there's so many different systems that have to keep working to make sure that it stays up and running. Yeah.
So I think engineering is about solving problems, and sometimes there's multiple ways to solve a problem. And what I'm curious is, you took one approach to solving a problem within some constraints that we gave you. So is there a different way now that you've learned what you have through this experience that you would solve this problem, and what might that be?
I think we're pretty proud of the way that we solve this. I think it feels very kind of straightforward in a way, where we pull data from the site itself, and then we send the data where it needs to go to be classified and displayed. And that is this is, I think, the most efficient way we could think of doing it. I think we're pretty proud of the choices that we made over the course of this project.
And then also, we did have constraints for it to be non-invasive. If you can see that picture, that's a diagram that we found at the site. All of the things that we could have connected to were inside the HVAC system, and would have to be pretty invasive to sense anything directly from the HVAC system. So this was the general way that we did it. Was really the only way that we could find to do a non-invasive system, was to have outside sensors.
So then I have a follow-up for you. What constraint, if we could eliminate one, would have made it easier to get the best solution you think would have worked?
Yeah, I think more data would have helped a lot with the machine learning, because we weren't able to fully customize the machine learning algorithm or really fully test it, because we didn't have data for this specific application.
And then in terms of connectivity, I think drilling a hole through the wall and having an antenna go out would solve a lot of our connectivity issues. So I think that would be helpful. I would say Azure services can be a little finicky sometimes, so maybe using AWS or a different service would be a little bit helpful, but yeah.
Any last questions for the team? Yes, Jim. Go to
So explain to me the machine learning part of it. So I mean, what I thought I heard was that you would be monitoring the acoustics of the HVAC system, and then you would learn what's sort of normal condition, and then if it fell outside the normal condition, then you would generate an alarm. Is that correct?
So essentially, yes. We're going to feed all of the sensor data into the machine learning algorithm. So not only would it generate an alarm for unusual noise, it would also for unusual power use, or temperature, humidity, and pressure. And then the alarm would be an email alert that would say you might want to look into sending a work order generation, or sending in a work order.
So what about this condition where the system's failing slowly over time? So what happens is the bearings are getting a little noisier, a little noisier, a little noisier. Is your machine learning algorithm then going to just consider that it keeps learning what the new baseline is? And so unless it's a sudden failure, then you wouldn't be aware of that the bearings are actually failing in the unit? or is there some sort of threshold that once you exceed a certain threshold, then it generates an alarm regardless?
So
So the nice thing about machine learning is with a large enough data set, you that unless it was truly failing over like a full 2 or 3 years, and like it continually over that 2 or 3 years was failing, it would be able to pick up on it regardless. So even if it took a month for this machine learning algorithm, or not the machine learning algorithm, for the HVAC system to kind of slowly degrade, or I don't know, more than 2 months, 3 months, whatever it might be, the machine learning algorithm is built to detect, like, even if it's kind of slowly merging that way, it doesn't really matter to it what sort of difference it is. It matters to it, or difference it is from the previous point. It only matters from the elliptical envelope that we're fitting to all of the data. So there are always going to be some amount of anomalous value, and it will be up to next year's team, once that data is collected, to specialize this algorithm to what amount of abnormality is the cautionary and dangerous values.
All right, so it is time for us to move on to the next team. Thank you.
Hello, everyone. We are ECE 23.3, and we are presenting today on our interactive load profile archive we built for our sponsor, KiloWatts for Humanity. So first, an introduction to the team. My name is Caleb, and I'm part of the hardware team.
My name is Brian, also part of the hardware team.
My name is Lawan. I'm part of the software team.
And I'm Adrian, and I'm part of the software team.
And our faculty advisor and company liaison. Our liaison is Daniel Nausner. He is a CLU alumnus, class of 2014, and co-lead of the microgrid team at KWH. Our faculty advisor is Dr. Miguel, ECE department chair and a professor of ECE.
Our sponsor is KiloWatts for Humanity, or KWH. What they do is they reach out to communities that don't have access to electricity and provide them a way to create their own electricity by building a off-grid power system. They also provide ways for them to use this electricity so that it's not going to waste.
So the problem statement we were given by KWH was that we were to collect data using the OGLAD, the off-grid load analyzing device built by the previous year's team, and process this data into individual device load profiles that could then be combined using the software portion, which was built off of a piece of software that last year's team built as a stretch goal, to enable us to build a combined load profile to represent a business or a home. And this will be used for planning their future microgrids.
Some of the specific things they want us to pay attention to include peak load, average load, as well as the hourly breakdowns for the data, as well as making sure that as we make enhancements and changes to the LGUI, that we maintain an intuitive design. As well, making sure that the combined load profiles that the program will allow will then be able to be exported to Homer, which is a software used by KWH in order to determine how best to build these off-grid power systems. A little bit more information about what a load profile is that load profiles are collections of power data over a span of time. And these can be for anywhere from just a singular device to buildings or cities. And in our case, we are only doing load profiles for singular devices. And so as we can take a look at some of these examples to get a better idea of how exactly load profiles work. If, for instance, for a household, people might not be at the house for most of the day, they might be out working, but then when everybody is coming home, you can see that there's a large spike since now electronics are being more actively used than the rest of the day, and thus there's a much greater power draw.
So our solution, as I said before, was built off of the very nice framework that last year's team built. They started the program in C#, and we decided to continue with this, as it's a very nice coding language for creating Windows applications. It takes care of a lot of the overhead and little details that you'd have to get into using something like C++. And building it off of the Ligui 1.0 also saved us a lot of trouble in building the basics, the menus, the start screen, all that.
A quick overview of how all of these systems will interact. So first we have the OGLAD, which is a hardware, and it takes US standard power alongside a USB stick in order to contain the data, as well as the device that we are measuring data for. We then save all of the data that the OGLAD generates in a device library, which is a piece of software, and the Ligui will then be able to access this device library in order to see all the data. As well, the Ligui will then be able to export any load information that the user would like into the Homer. So the budget for our project only contained two things, which are 2 Homer licenses, as KWH provided any of the devices that we would be testing, thus we did not need to purchase any of them.
So to go over a few milestones in our project, the first milestone and an ongoing one was the data collection. We weren't tasked with collecting a specific amount of data, so this sort of just went on until the project ended, got as much as we could. We also had to figure out how to store the database of devices within the software. We will talk about our solution a little bit later on that. We then had to plot the sum of the data, those combined load profiles, over a 24-hour span, which is useful for finding the peaks, the lows. And formatting that microgrid load profile report, that's the file that gets exported for use in Homer, as well as general software things like UX testing, user experience testing, make sure there are no bugs, make sure everything can run smoothly, it works well with KWH's process, and generating a user guide just to walk them through the software and make sure they know what they're doing. Initially, we did have some accuracy issues with data collection. We finally resolved these, and we believe the problem was a few loose connections inside the OGLAD, as they were resolved after a full rebuild, tightening all the connectors and all that. And so that will have to be monitored for future use of the OGLAD, but it is a pretty quick fix because they're all, none of them are screwed in or anything. We also decided on a format for the data within the software. For continuous devices, these would be things like lights and fans that you're going to be running at a pretty constant power usage for a longer period of time. All you need in the software is the name and the average power. So you can take that CSV file that the OGLAD outputs and just input it directly into the software, and it'll calculate that for you. For a non-continuous device, this would be something like a dishwasher or maybe a welder that is running at peaks and lows. This is something that you need a little more detail on. For this, you would need a name, the power when it's running, the power when it's not running, and the duty cycle, or how long it's on and how long it's off. We also created a procedure for data collection. This is included in the user manual for the Ligui, but this is just to make data collection with the OGLAD more consistent and to help the Ligui run smoother. It says things like to make sure you're collecting data only when the device is on, and various other things like that.
So to start out with our team on the software side, some of our first progress was to do some cosmetic changes. And this was kind of familiarizing ourselves with Visual Studio, C#, and the previous team's build of LaGUI 1.0. So here's a little detail of how we changed some of the colors around and kind of gave us an idea of where we would take the code next.
Here's what it would look like if a user were to use the LaGUI 2.0 and all the new functionalities that we've implemented. So first, on the LaGUI home screen, users can click File, Save Device As. Once they click this, they'll be prompted to their File Explorer where they can choose the CSV file that has been exported from the OGLAD. And once they choose a file that is compatible, the LaGUI will ask them to enter a device name for that device. In here, the LaGUI will also check to ensure that the user enters a valid name. So this means just letters, numbers, underscores, no any weird symbols. And this will also double check to make sure that there isn't a device already existing in the library with the same name. This is just to limit any confusion later on when the user actually interacts with the library. Once they enter a valid device name, they'll be asked whether or not the device is continuous or not. So if the device is continuous, the LaGUI will just calculate the average apparent and active power for that device. As Caleb mentioned earlier, for continuous devices, it's a pretty much constant power usage, and so we can calculate the average pretty easily for that. However, for non-continuous devices like a microwave or a dishwasher where something is plugged in continuously but it'll only spike up if it's in use, it's a little bit different to calculate the average power for that, because if you're just calculating the entire average, you'll get a very inaccurate value for the actual power usage. And so to fix this problem, we created a threshold limit of 3 watts. And so if the non-continuous power goes below 3 watts, it will be excluded from the final average value. And this is just to provide a more accurate representation of the device in use. After the user enters whether or not the device is continuous or not, they'll be notified that their device has been saved. When a device is saved, it gets appended to a CSV file that is located in the resources folder of the software. Here's an example of what the CSV file looks like. It has the device name, the type, and the average apparent and active powers. And this is located in the resources folder, so the users can access this device library using their laptop or computer, whatever device they're using, and they're also able to exchange device libraries. Because KWH works with communities in sub-Saharan Africa, if someone's working in America and someone's working in Africa, they're able to exchange device libraries and see each other's data. For the CSV file, you're also able to append and delete devices. This could be done using the LaGUI itself, which I'll show you in a little bit, or just accessing that CSV file and deleting the row. For the LaGUI library screen, on the left-hand side, we have the list of devices that a user has previously saved. It will appear on this box. If you click on a device, the device's data will be showed in the box right next to it. On the bottom left here, you can see there's a delete device button, and this will permanently delete a device from the library if the user does not want a device or there's been a mistake in the device's data. They can delete the device. It will delete it from the library catalog on the LaGUI and also in that CSV file I showed you in the previous slide. For load profiles, users can click Add Device and Remove, and it will append devices into this box right here on the right-hand side. And again, users can click on device in their load profile, and the device's data will show in the box on the most right-hand side here. On the library window, the user has the option to click New and Open. If they click New, if anything has been in these boxes, it will clear out. Or they can click Open and open a previously saved device or previously saved load profile that they've created to make any edit or changes if they wish to. Once they create a load profile, they can click Save and Save As. It'll take them to their file explorer like any other application, and they're able to save it on their device that they're using. When they save a load profile, it'll create a CSV file that looks like this. It has the same data, so name, type, and the average active and apparent powers. And this file can then be imported into the grid load.
So to talk about grid load, right here is an overview of what that window would look like. To break down the top, there's a bunch of analytical data that you can get from your load profile. It has the list of devices at the top left. Next would be the device's data for how much power it is. Right next to it is where you would set the hour on and hour off in a 24-hour period. That basically sets its cycle for usage. And then you're able to graph the apparent and active power from that load profile. Right next to it is our Homer CSV tables. These right here will show you the total accumulated power for that entire day from 0 to 23, and it also gives you an idea of how much power is actually being used. That's also all what's graphed on the chart, which was on the previous slide. And right next to it is also our peak and average powers for apparent and active for that load profile. So this is your composite load profile. Once you've set all the time, you can see that the graph shows active and apparent data. This basically allows you to export this graph so that way you have a visual representation of what your microgrid system would be using. On top of that, you're able to save this load profile, which would be separate from the others. It's a CSV file for the microgrid, and you're also able to update it and make multiple generations of this. Here's what the grid load CSV file would look like. There's 2 additional columns that are added, hour on and hour off. These would be your times for when the device is in use. Next would be our Homer file. This is what's exported so that way KWH can build their actual microgrid systems. It goes from hour 0 to 23, and on the left would be the hours of the day. On the right is the total power in kilowatts for that hour section.
Lastly, we have the Lagui test plan, which is a detailed procedure that we wrote and provided to the sponsor along with the software. It contains 2 main components: user experience and software functional testing. The user experience testing contains a checklist of items to ensure that our system satisfies the requirements of navigability, effectiveness, efficiency, usability, along with an intuitive design. This means that it's easy to navigate the application, the buttons are easy to click, the font is legible, and the colors don't contrast too much. For the software functional portion, we had 2 types of testing: unit testing and integration testing. The unit testing was a procedure that the testers can follow to make sure that we implemented all of our functions correctly and everything works accordingly. This means when you click on the library window, that library window will pop up, contain that list of devices that a user has previously saved. If you click on the grid load window, the grid load window will be able to appear. Our integration testing portion is another procedure that the testers can follow to ensure that our software is compatible with file types and data inputs. This means that you're able to import saved data, you can graph the saved data, you can save load profiles. Overall, our Lagui test plan's goal was to ensure that our testers were able to test all the functions that we've implemented and to make sure that they're able to find any bugs that may have required fixing. Questions?
Any questions there?
I'm a little confused about the terms that you used up there related to power and apparent power. Because to me, VA is almost always higher than actual watts, because watts is VA times power factor. So could you explain that, please?
Yeah, so I was kind of hoping nobody would notice that. I only just noticed it myself. I believe that's data from before we fixed the accuracy issues. That was one of the big problems we were having, was any device that has a really high inductance, like a DC motor or an AC motor, was causing issues with the active and apparent power. My guess would be something like it was reading the reactive power backwards, but we didn't pinpoint exactly why it was happening. So I think that was old data.
Okay, so the goal is that you are determining that the actual volts and amps, right? Because that'll depend on the size, if you're going to size whatever your source is, you need to consider both, not just the actual watts.
Yeah.
So.
Hey, I just wanted to thank the team. I think this is probably the most niche project we've had a Seattle U team build something for us, but looking forward to kind of having a more repeatable and a more consistent experience with sizing our system. So thanks a lot, team.
Thank you.
I just want to preface by saying that your guys' design for the Lagui looks really great. And it kind of warms my heart seeing it from last year's. Just the big improvements that were made, just visually look really great, and the functionality I can only assume gets better from there. So I think one of the things that I would like to know was that there was a big problem with large data sets going into the Lagui from last year. And I did see some issues, I guess, that was brought up previously in the early, beginnings of phases of testing it. How was that reconciled? And for the data sets that KWH kind of takes up with all the different loads that they measure, how well does it do with those large data sets versus maybe you're just measuring a load for an hour versus a 24-hour? So to speak.
So initially for our system, we've decided to kind of restrict, especially with our test plan and recording plan, we've restricted it down to about an hour of usage unless it needs to necessarily extend past there, rather than testing for a full 24-hour period. And it kind of gave us a little bit more of an accurate representation when building that composite load profile.
Also, to kind of make up for that, for our load profiles, you're able to add multiple devices. So if a device is on for more than an hour, you can add multiple devices and enter the time that it's on, and so that you're able to have it throughout different parts of the day instead of having duty cycles, which would make it a lot more difficult, especially for non-continuous devices.
We have time for a few more questions. Maybe I can ask a question. So for each of you, what would you say was the most valuable lesson learned during this 9-month experience that you had?
So I learned that diagnosing hardware issues, especially in something that you didn't build from scratch, can be very hard. Finding what's wrong in a box with very little feedback is difficult.
For the software side on my end, I think it was trying to come up with an effective way to divide up the work. Doing Visual Studio Live Share was not very effective on trying to compile together and make changes. So at the same time, Loan and I took turns on deciding who would take the software and what portion they would do, and then sending it back and forth. That kind of created an effective way to make sure we had a status quo for the software.
I guess for me, it was also trying to make sure that the hardware and software team were on the same page and kind of knowing where each one was going and being able to make sure that we can support each other, since we are supposed to be one team, not two separate teams.
I think for mine is that coding doesn't have to be hard unless you make it hard. Coming into the project in fall quarter, me and Adrian didn't have that much experience using C#, especially because we're from the EC department. We worked a lot with C++ with hardware. And so we didn't have that much experience with C#. And so that was a learning curve. But also when we looked at the Lagui from the previous year, it was very overwhelming because we've never seen application code before. And there was a lot of code. There was one file in particular that had over 1,000 lines of code. And so me and Adrian were definitely a bit overwhelmed just trying to decipher what everything meant and what everything did, what all the forms did. And so, but it wasn't hard. So after we took a couple days to read it through, we realized that a lot of these functions are simple. Visual Studio, because C# is created by Microsoft, it was a really great application to use. It was a really easy code to use, and it was overall, I think, not a bad experience when we actually got to implementing all of our functions.
There's a question for the hardware people. Is there an area that you'd wished you knew more about after this project?
So I would say data collection or power data collection in general. It really would have helped us figure out all the errors at start instead of just trial and error trying to fix things. There are still small amounts of error, but they were deemed negligible enough. So there's still some sources, and I wish we knew why.
I mean, yeah, basically just, knowing more about like the data side of things and being able to better diagnose the like potential issues. So, yeah.
Thank you. If there are no other questions, we can thank the team. And if you do have questions for either of the teams that presented in this session, please find them at the poster session, which begins at 4:15. Thank you. Good afternoon and welcome back. We have 3 presentations scheduled for this session, the sponsors being Amazon and AWS. A quick reminder before we begin with the presentations, there will be time for question and answers after each presentation. For our live audience, if you have any questions, please raise your hands and I'll bring the mic to you. This is so that our online audience can hear your questions as well. And for our online audience, if you have any questions, please type them in the chat window and we'll get to them. I'll hand it over to the team now.
Hello, and thank you for joining us this afternoon. We are Team CS2301 with Amazon Alexa. Today, we'll be presenting our capstone project. Now, before we get started, this presentation does contain profanity. So if you feel uncomfortable, please feel free to exit the room at any time. During this presentation, we'll be covering an overview of our project accomplishments and challenges, followed by an interactive demo. And then we'll also follow up with our plans moving forward, as well as the impact of our project. My name is Gary Tu.
My name is Isabella Wallace.
My name is William Somat.
I'm Jacob. I'm Blaise Naranyabagira.
And for the rest of our team, we have Sheila, who is our faculty advisor here at Seattle University, along with our primary sponsor at Amazon Alexa, Sundar, who's the principal PMT for Alexa's experiences. And we also have our stakeholder, Roshanak, who is also a principal PMT for Amazon Alexa Experience. And she was also the department chair of CS a few years back. We welcome you back. And we also have our 2 primary engineering contacts, Vijay and Vishan.
Our sponsor is Amazon, the creator of Alexa. We are part of the trust and privacy team, specifically ASCII, Alexa's Sensitive Content Intelligence. And ASCII is responsible for filtering out responses and identifying sensitive contents within Alexa's traffic. Alexa have many different devices. Some are auditory only, such as the Alexa Dot, and some are auditory and visual, such as the Alexa Show. Amazon Alexa may use contents outside of Amazon, such as the internet, news articles, blog posts, YouTube, or other user-generated contents, and it may contain the use of profane words. Amazon wants to prevent Alexa from using or showing the profane words to customers because Amazon wants to avoid headlines like these, where a kid asked Alexa for a TikTok challenge and Alexa responded with a dangerous TikTok challenge, or another where a man claimed that Alexa was swearing at him.
And so why focus on this opportunity? Well, by minimizing sensitive content and profanity that is used in Alexa's answers, we maintain customer trust and increase customer trust. Additionally, we want to preserve and maintain the brand reputation. And all in all, we want to continue to foster and improve positive customer experience with Amazon Alexa.
Our project has 2 main objectives. The first one is to detect variations of disallowed words and phrases, such as duplicative letters or misspelling of letters. And examples of that can be seen here on the screen. The second one is to detect vulgar-sounding phonetic pronunciations of phrases. An example of that would be taking the words sofa and king. With phonetic sounding, it might sound like so fucking instead of sofa and king separately. For our solution, we created an API, an application programming interface, and we designed it to detect text-based sensitive content inputs. And we designed it using Go language. And the way we do that is through these 6 use cases that we came up with. We want to be able to detect profane words with minor misspelling of letters. We want to be able to detect profane words with all 3 levels of lead speak, and we'll get into that at a later slide. We want to be able to detect profane words with duplicative letters. And we also want to be able to detect profane words with phonetic sounding contents. Lastly, our design will return a Boolean value with its offending contents and its policy violation.
So for our deliverables, on top of the API, we have to deliver the GitHub repository for our code. So, and on top of that, we have to deliver our documentation so the stakeholders or any other internal Amazon teams can go through the code, understand our approach, and maybe later improve our system. We broke down the project in 3 major milestones, and those 3 milestones were accordingly matched with the 3 quarters of the year. For 4th quarter and the first milestone, we have creating the documentation for the project and all the planning documentation, and setting up our backlog with the tasks based on our use cases. For the 2nd quarter, we have solving the first 5 use cases. That means misspelling, duplicates, and lead speak, and setting up unit testing. For the 3rd quarter, we have our 3rd milestone, which was about solving phonetics, and then creating the project day deliverables, and also doing more documentation about the API. When it comes to project methodology, we adopted agile principles. We broke down our project into 12 sprints. Each sprint was 2 weeks long. And our backlog tasks were all based on the 6 use cases that we defined.
Yes, I'll go over use cases 1 through 5. So the primary goal of it was for number 1, to detect leet speak. And for reference, leet speak is sort of this internet slang way of typing and spelling things. And so it has 3 different levels. Level 1, you replace pronouns with numbers. Level 2, you go a little bit higher and you pronounce consonants with numbers and symbols. And then level 3, you combine 1 and 2, and then you also just sort of start replacing anything with everything, and it gets really complicated. We also have misspelled words and repeated letters, which are also goals of 1 through 5.
So when it comes to solving use cases 1 through 5, which are leet speak, misspelled words, and duplicate letters, we need to understand the similarity between words. So for example, if we have the words cat and rat, we want to quantify how similar they are. To do this, we use Levenshtein's distance algorithm. Levenshtein's distance is an algorithm that computes the edit distance between 2 words. This is the number of modifications, such as insertions, deletions, or replacements necessary to transform one word to another. So for example, the edit distance of cat and rat would be 1 because you just need to change the C to an R. Now, we want to use this to transform each word in Alexa's traffic to a list of known profanity. And using Levenshtein's distance, we can create a scoring system, which represents the similarity between words. This is essentially the percentage of similar characters within the 2 words. And a score of 1 would mean that they're identical. However, before computing the score, we need to do some pre-processing first. And that's mainly because of our use case 5, which is repeating characters. For example, if you have the word shit with 20 T's, it'll have a great distance compared to shit properly spelled. So we remove any 3 or more consecutive repeating characters and reduce it down to 1 instance. And that's because in the English language, there's a rule where words cannot have more than 2 instances of repeating consecutive letters. So this cleaned version, which also has punctuations removed, is then given to our scoring system. And when it comes to phonetics, which is our use case 6, we need to understand how similar 2 words are phonetically. And for this, a lot of phonetic algorithms will give us the phonetic representation of words. And we use them because a lot of them were developed specifically for English or Latin-based languages. And many of them were also made for matching names.
And so there's a variety of phonetic algorithms we decided to look at when trying to look at our use case 6. And so we focused on 16 different phonetic algorithms, as you can see here. And there were a couple of factors we were going to look at to review these phonetic algorithms in order to choose some to implement. And so one of the factors that we looked at was fuzziness. And Jacob will discuss about what fuzziness is when it comes to a phonetic algorithm.
Yeah, so fuzziness was a very big key player in our phonetic algorithm. And so what fuzziness is essentially how much you approximate the phonetic representation of a word. And so if you have a word that is too fuzzy, you'll get false positives. So for example, if bitch equals witch, that is a false positive, you don't want that. But you can also get vice versa, where if it's not fuzzy enough, you'll get false negatives where FUCK does not equal FPHUCK, where they should be pronounced phonetically the same, but if it's not fuzzy enough, then you'll get a mismatch.
So this is our 3 phonetic algorithms that we chose. Keep in mind that for our phonetic package, an input would have to be detected by all 3 phonetic algorithms for it to work. If not, it will pass through undetected. The first one is the double metaphone algorithm. And this algorithm is based off of the original metaphone algorithm. And it is best used for single words based on their pronunciation. The second one is the New York algorithm. This algorithm was originally created for detecting names for the state of New York, but it can be used for other things such as substrings, phrases, and single words as well. The last one is the Cologne phonetics algorithm. This is an open source algorithm that is used to encode words based on their pronunciation. This algorithm assigns words to a sequence of digits, and it can also make identical sounding words to have the same sequence or codes.
Okay, so I'll go over our high-level architecture diagram. So at the top left, it all starts with the customer, and when they ask Alexa a question, that question will then get routed into internal Amazon Alexa traffic. And within that traffic, eventually it'll reach the ASCII team, and the ASCII team is responsible for removing profanity. So then they will contact our API, which is on the right side. And from our API at the top is the detect package, which is the main orchestrator package. And it orchestrates the lead speak and the phonetic package. And the lead speak package is responsible for catching variations of profanity. And the phonetic package is responsible for detecting phonetic variations of profanity. And at the bottom of it, we have our dictionary, which both packages interface with, which defines what profanity actually is. And in a larger scope, we have the possibility of interacting with other Amazon services that also need profanity detection.
So blockers, we were lucky to not run into many of them, but obviously we couldn't escape all of them. We had 2 major blockers, and as we are a competent team, we were able to overcome them. So our first major blocker was the fact that we were facing a limited data for testing, due to the fact that in this kind of domain, most data is just private for most companies. So our solution was to just generate our own data. So we created our own data sets, and that's what we used to test our features. Our second blocker was that we were wishing to deploy this system on the internal Amazon infrastructure, and that's the AWS. But due to the time requirements that it took, and we did not have that time on our hands, so we just left that task to the internal Amazon team and just submit our system the way it is. We are happy to announce that we're able to complete all our milestones. That means we're able to create the REST API. We're able to solve all of our use cases. That's misspelling, duplicates, lead speak, and phonetics. We are also able to set up automated testing. On top of that, we were able to create a website where we can demonstrate our service capabilities.
Alrighty, yeah, so it's time for the demo. So if you happen to have your laptop with you, now's a great time to pull it out. Otherwise, you can take your phone and scan this QR code here. The URL is amazon.guarantee.com. It's also written on the whiteboards too. I'll give you guys a second to do that. Alrighty, so this here is what the website looks like. So as you can see, we have a text input. Within this text input, you can put anything you'd like, including profanity or variations of profanity. And if we scroll down and click this Detect Profanity button, we'll see that instances of profanity have been detected. And if we were to click on the highlighted profanity, we can see how it was detected. So for example, this specific instance here was detected by both the phonetic and leet speak strategies that we have within our code base. And while testing, we also love to run longer content through it. So for example, Wolf of Wall Street has a ton of profanity in it. So if we were to copy and paste that in and run it, we can see that there are many instances of profanity that were detected by our system. Amazon had a goal for us to respond within 40 milliseconds for normal Amazon traffic, which are short questions or short responses. However, even for the super long movie script, we can see that it's responded within 100 milliseconds, which is relatively quick. And that concludes this demonstration. You guys can continue playing along on your phones.
So with all that, to wrap up, we had a lot of major lessons and advice to any future capstone students that I do see here. And so I'll just talk about this first one right here is visibility of your teammates' work and just making sure that you and your sponsor and your advisor are all on the same page on what tasks are being done, who is doing them, what the progress is, and additionally just having that transparency. It just allows you to advocate for yourself. It allows you to advocate for your teammates, allows you to advocate your team to your sponsor, because there might be a disconnect between what your sponsor wants and what the team is able to produce in whatever deadline you have. And so just making sure that everyone is on the same page on the work that you are doing can just ultimately lead to high quality work.
So for future recommendations for the project, our first is more research into phonetic algorithms. We covered a lot of them, but there's still more out there, and also maybe a deeper analytical approach to the ones that we did find success in. Number two would be lemmatization. Lemmatization is the act of removing suffixes from words, so like ing, ed, er. And so when you remove these from words, it sort of standardizes them and helps prevent false positives, false negatives, and improves performance. And lastly, we have machine learning. Our phonetic solution feels like we're trying to fit a square peg into a round hole, and it just doesn't really feel like the correct solution. So we think perhaps a more dynamic approach with machine learning would fit the problem better. For what's next, we have to turn over our project deliverables to Amazon. They can figure out how they want to incorporate into the Amazon Alexa framework, and also more research into phonetics, as I said.
Thank you for joining us today. That concludes our presentation, and we'd be happy to take any questions.
You had 16 phonetic algorithms that you initially looked into. How did you choose 3 to continue with?
So we had 3 main factors that we looked at. So the first one that we decided to touch upon was fuzziness, and that Jacob explained. It was how stringent or lax the algorithm was when comparing 2 different sounding syllables. Another factor was the type of result the phonetic algorithm returned. So during our research, we discovered that there was 2 different types of phonetic algorithms. There are string results algorithms, and hash results algorithms. The issue with hash results algorithms is that you cannot use it to do comparisons with like a similar comparison. With hash base, it was like a string of words or a string of numbers, or sometimes a mixture of characters and numbers. And you can't, with a hash-based algorithm, you can't really you can't really quantify how similar one output of the phonetic spelling of one word compared to another word with those types of algorithms. You can do it with a string result, and that way we can use Levitstein's distance, which we already use as a way to compare likeness between two phrases, two words, etc.
Yeah, and one way to think about this is that with string results, you get essentially a number of how similar they are, a number between 0 and 1. However, with hash-based results, you get a Boolean, which is a yes or no. There's no similarity. It's either it matches or it doesn't, which is not what we're looking for. String results give us more information.
So you said you had limited access to a data set and you generated your own data set yourselves. How did you generate your own data set yourself?
So we were able to scrape around the internet, and our stakeholders were able to provide us with a little bit of data. So we just built from that and build like sentences and try to expand all those words on top of words that were already existing from the dictionary. And that's how we just made our data sets.
And a follow-up question, right? With the data set and with the algorithms you used to test if a word was profane or not, right? Did you pick up alternative algorithms to sort of compare the effectiveness or the accuracy when you have a profane word?
Right, that's a great question. So with our data set, we had split the data set into two categories. We have positive cases and negative cases. So positive cases are cases where it should match. In other words, like FUCK and PHUCK that we saw on the screen earlier, that's a positive case, they should match. However, we also have negative cases where they should not match. So using these two categories, we're able to compute the false positive, false negative, true positive, true negative. And with that, we get the accuracy, recall, and precision. So these are metrics that we can use to determine how accurate each individual algorithm is.
So your data sets look to be like very standardized profane kind of use cases, right? But as we know that like within society, we have linguistics and it develops, and the content sensitivity looks to be tailored to maybe young kids, Gen Z, who are using maybe language that hasn't been so standard. What are like some considerations for future, I guess, developments of this API to account for the development of maybe slang words that younger people are using that maybe people who are older might not be able to recognize and thus not implement and consider going forward?
Yeah, so currently we just have like a list of profane terms, and you can really update it whenever you want. So I suppose someone at Amazon would be responsible of taking charge of what they consider profane and not. And that's sort of more of like a long-term issue, I guess, more than like a design one for us currently.
As a follow-up to that, do you foresee it causing issues with, I guess in your example, but bitch and witch, right? The idea of like witch is not necessarily something that is foreseen as like a negative term, but with the development of language, maybe as like young slang might see it, it could be used as like, hey, sick is like, it's a negative like connotation, like something is sick versus like, hey, this is really sick. Like, how are we able to like differentiate between like that kind of barrier?
Yeah, that's a great question. So with our program, we have two data sets, and one of them is a list of profanity. And if I'm able to share this, the current Amazon implementation is a list of rules. They're all it's both ML and rule based. So right now, if there is a case where that needs to be filtered, we would need to add a new rule. So that's kind of similar to what we have going on here, except ours is able to take multiple variations of it.
It is time for us to move on to the next presentation. Let's thank the team.
Hello, everyone. We're Team ECE 23.1, and our project is the second iteration of the AWS Availability Rover Cart. So for our agenda, we're going to be going over the team sponsor and liaison introduction. We're then going to be going over our goal, solution, and design. And finally, we're going to end with a short Q&A session. As for the team members, we have Chin, Jim, Logan, and me, Ken. As for our faculty advisor, we have Dr. Alvin Moser. Also, for this year, we're working with the mechanical engineering team, ME 23.1. And for our team liaison, we have Mike Tran. He's the mechanical engineering team liaison, and we have Derek Bennett right there. He's our team liaison.
So our sponsor is Amazon Web Services, or AWS. They provide flexible, high-performance computing to businesses around the world through their cloud. The problem statement that AWS decided to give to us this year is to improve upon a previous iteration, which was developed by last year's team. And the requirements for this cart is that it had to be mobile enough to be pushed through a data center. It had to have location tracking without GPS or Wi-Fi. And most importantly, it had to be able to collect different types of data from different types of sensors simultaneously. The data that was to be collected is barcodes, thermal images, and a full audio spectrum, including ultrasonic.
As for our goals and specification, we have to replace all of the visual cameras with barcode readers for localization purposes. We have to also rework on the thermal imaging software and add audio sensors for frequency analysis and to warn the user if the environment is too loud. We also have to create a database to be able to store all of the data in. And as for a stretch goal, we have to implement the LiDAR mapping and improve on the previous team's user interface.
For the computation hardware, we had several sensors that are continuously taking in data, analog, digital, and other systems. Because this is continuous and because the data is being processed, it made sense to break down into three separate categories: the microcontrollers that would continuously read and then push through the USB to a laptop that had a database, and then a microcomputer, which is a Raspberry Pi, to do the motor controller, again, ultimately push through the laptop. This way the laptop can be collecting data into the database without being labor intensive for data processing.
So the first sensor that we're going to be talking about today are barcode readers. So the previous team had a solution to the barcodes, but the problem was that it used actual visual cameras instead of barcode readers, and that presented a security risk to Amazon. It also made the cart a lot heavier than it needed to be, and it also had to be manually operated with a eye-leveled laser pointer. So the solution that we're implementing uses the actual barcode readers, and that solves all of the problems that the previous team had. So the hardware setup for the barcode readers is very simple. We have two barcode readers which feed into a USB hub, which then sends the signals and data into the laptop. The software diagram likewise mirrors that, and we have the two barcode readers feeding into a data processor, which is onboard the laptop. From there, everything is stored onto a MySQL database, also onboard the laptop. The methodology of the barcode readers is very simple. So when we scan something, all of the gathered data that is taken when that is scanned becomes associated with that barcode. Rescanning that same barcode will bring up the gathered data. So for example, if you take a barcode scan with a thermal image, rescanning it will bring up that thermal image.
Next up, we have the thermal cameras. So last year's teams have already implemented a solution for the thermal imaging system.
So we have decided to reuse the system with a few modifications. So on the screen right now is a thermal camera. It is provided to us by AWS. It uses a vendor software to capture the images, and the images would then be stored into the database. Here's the hardware diagram. We have 3 thermal cameras connected to the laptop using Ethernet. As for the software side of things, the 3 thermal cameras will capture the images, and the images will then be stored into the database. Here's how the whole thermal imaging system works. 2 thermal cameras, one on each side of the card, will capture the thermal images of the servers, and whereas the one in the middle will capture the thermal images of the environment inside the data center. And then the thermal images will then be uploaded to the database using our Python code.
As for the sonic microphone, this is still currently in implementation phase. We have the Adafruit electret microphone. It got an adjustable gain, an analog output that scales with the power supply, and it got a frequency response across the human hearing range. As for the methodology, from the left here, we have the microphone outputting analog signal to the ADC. The ADC then converts the data into digital data and then store it into the DMA. The core then retrieves it, process it, and then send it to the database on the laptop to be stored locally via USB. We have also verified the functionality of the ADC and FFT with waveform generator. And we have pretty much verified the whole system functionality with a speaker. However, we still have yet to mount it on the card. As for the ultrasonic microphone, this is also still in the implementation phase. We have the Graph 46BD. This one goes all the way up to 100 kilohertz, and however, it requires a power module in order to drive it, the Graph 12AL. Now, as for the methodology, since the power module outputs a very weak AC signal, we would have to amplify it and then shift the whole waveform into the DC range for it to be compatible with the ADC and for it to be easily readable. So we end up creating an amplifier circuit that has a 71 gain. And we also created a framework for us to be able to convert the ADC value reading directly to the sound pressure level in decibel. Finally, we also have programmed the software for us to process the data and then get the frequency values and then upload it to the server.
There's an array of environmental sensors that all are on an I2C hub bus, which is nice. And because several of the sensors have the same address, we were able to use a hub and then rotate through. So this saved on software. And so we have things like the time of flight sensors in case the cart gets too close to the walls. It will send a signal, it's measuring the distance. And then there's a pressure, humidity, and temperature sensor to monitor the environment inside the data center. So all the sensors route into the I2C hub. So this is kind of the hardware flow diagram, as well as the temp. The hub drops into the I2C and can be set up to feed into the DMA, which is the direct memory access. And the nice thing about doing it this way is it leaves the processor free until it's time to actually do a computation of the data and analyze it before sending it off to the computer via USB. And the nice thing too with the microcontrollers is once the card is on, all the hardware is initialized and then it just runs. And so you're not having to wait for things to kick on or turn off or communication. It's just continuously running and collecting data. It has pass-fail criteria. If it fails, it alerts the operator and keeps collecting data to be continuous, because you don't want to like stop the system if you don't have to unnecessarily. There's a lot of drivers for all the sensors that need to be written, and to me it's very important that when you write a driver that it be portable. So the drivers are written in C, and if they need microcontroller type needs to change in the future, that can take place. We did find that the temperature sensor we got from the manufacturer had a hardware bug, and we were able to fix that and then continue moving forward. Linear actuators, There's two on either side of the cart, a set of 60 inches for the base and then a 30-inch set. So we use the Pi hat. We went with the Raspberry Pi because we could use the Pi hats and make a really nice stack for all the motor controls and proximity sensors. And we also wanted to control it with the joystick and a button. And I will let Ken talk about the software.
As for the methodology, it may be a little bit hard to see, but the diagrams on the pictures on the left, we basically have two motors, one on top of each other, so that they can traverse the whole server height. And to be able to control it, we programmed a joystick so that if you push it forward, it's going to move the platform up, and if you pull it back, it's going to move it down. Now, in order to give the control to the other side, we also added a button. So if you press it, it's gonna switch the control to the other side, and if you do it again, it's gonna switch back. Now we also added another functionality. If you press on the joystick, it's gonna reset the platform, both platform to a predefined default level. This is to prevent the user, if they were moving the cart on an uneven terrain, it may hit the ground.
So our first stretch goal that we're going to be talking about is the LiDAR system. So we procured the A1 RP LiDAR sensor with the intent to use it on top of the cart. Unfortunately, due to time constraints, we never got around to actually implementing it. But we planned out how we were going to do it. So the LiDAR sensor would feed its data into a USB. That signal would then be going into the Raspberry Pi, which would then be fed into an Ethernet hub, which would then be connected to the laptop, and the data would be stored there.
Our next stretch goal is the user interface. So we have implemented a simple user interface to help the cart operator operate the cart and to collect data. So there are four main functionalities: scanning barcodes for location tracking, collecting data such as temperature, pressure, humidity, and time of flight. We also have an option to retrieve the data by having the cart operator scan or type in the barcodes that they want to see. And finally, we have a way to show the database. Now we'll be talking about the budget. So this is a CRU Project Center budget. They have been helping us throughout the project and buying us a lot of items for us to work on the project. And the total is roughly $1,000. AWS also supported us, and they also buy us equipment and tools, and the total is up to roughly $4,000.
It's very important to have good teamwork on this. The engineering is easy, the communication with your peers, not always. So I'm very proud that at the beginning, asked, people love to silo, and they silo by degree or department, and with the ME and the ECE teams, they said, hey, let's not do that. Let's work together, please. And these guys did an amazing job. So the photo on my right, your left, you can see the ME team is in the background, the ECE team is in the foreground. So we have sensors, and you can see we're making use of the whiteboards. I have homework. We all had homework. We're students. So I took mine home, and my son was helping me with mine, where in development, we could just push a button to go collect the data from all the sensors. And he's very happy. Midway through, once we started getting the cart from the ME team, they provided the frame. We were able to then test fit some of the stuff together. And again, like the big thing here was collaboration, that for 9 months, we had 9 people working together, talking, communicating, and I'm very proud of everybody for doing that. And then here we are at the data center outside. We cannot show you inside. It's top secret. But we got the cart assembled. So we had to assemble it here, test it, disassemble, transport it, reassemble, and then push into the data center for testing. Questions?
Questions?
All right.
Let's see, do we have questions from our online audience? Yeah? Okay. Last call. Any questions for the team? Yeah, so maybe I'll ask a question. So for each of you, if you could identify one key lesson that you learned throughout that 9-month senior design experience, what would it be for each of you?
For me, teamwork is very important. We have we have 4 members here, but we also work with the MV team, so we technically have 9 members. So, and it's a big group, and it's a big project, and so teamwork is very important. And I'm happy that everyone here is working together, and we deliver the project, and the liaisons seem to be happy. So.
I have quite a bit of industry experience, so I knew right away how to extract from the liaisons what it was they were looking for. And then I set the bar and asked everybody, what are you comfortable with? And we lowered the bar 1 rung, but it was still massive. And so the lesson for me was to better understand people's workloads and skill sets. And in the end, we all came through, but I know it was a lot, but we did it.
I think for me, it'd be that projects come together through clear communication. Was that yours? Oh, sorry. But yeah, there was a couple times where we had like several miscommunications between us and the project center, us and the ME team, and sometimes the liaisons. And being able to be open about being wrong about that was really useful in making sure that this project came together. Good luck.
Well, what he said.
All right, let's thank the team.
All right, we are the Mechanical Engineering 23.1 team, and our sponsor is Amazon Web Services. And we have Kai, Josh, myself, Weston, Albert, and Joseph. Our faculty advisor is Dr. Dad Farnia, and our initial liaisons are Mike Tran and Derek Bennett. So just to give you some background on the company, Amazon Web Services, or AWS, is a cloud computing service that has data centers that need to be running around the world, or all around the clock. Just kidding. We were just showing you what would happen if one of these servers were to go down. You wouldn't be able to access your data anymore. So what do these data centers actually do? Well, they house all the machinery or the components that the machines use to produce this cloud computing power. And every business needs these services because you need a website mainly for your company or project that you're doing. So you can sell products through Amazon and managerial operations and other web application that you need for your project. And the main draw for this is that Amazon is dealing with the maintenance of the servers and not the client, so they can focus more time and energy on their project or company. So who uses these servers? Well, pretty much all of your favorite tech companies, Amazon, or sorry, Instagram, Spotify, Netflix, your favorite apps and websites all use this. As far as some motivation for this project, we wanted to help maintenance workers in their day-to-day tasks. So this includes going around the data centers and collecting data on if the servers are running properly, if anything's malfunctioning or overheating. And we wanted to make this data collection process more efficient and more accurate for them to make their jobs easier. We wanted to optimize this process, making the whole thing smoother and quicker for them, and also the ultimate goal of optimizing this product in the end. And all of these things ultimately make data more accessible, leading for a reduction in monetary losses for Amazon.
For the 2022 cart, we learned that it was an off-the-shelf cart with a large footprint, and the sensors were all manually operated in a fixed location. It was a good proof of concept in the beginning to make sure that it actually works, but there can still be room for improvement. Moving on to the problem statement, as mentioned just now, we have improved upon the 2022 cart design. We started by building a new custom cart using a T-slot aluminum extrusion shown on the right to accommodate the increased range of vertical motions for the sensors to collect data, which spans around 7 feet, while keeping in mind that the cart footprint has to be reduced by 25% from last year's. Introduce automations on the lifting system and integrating new sensors around the cart with the electrical and computer engineering team.
So we can now move forward into talking about our year's cart. For the purpose of this presentation, we'll be referring to your right-hand side of the cart as the back or operator end, and to your left-hand side of the cart as the front end of the cart.
All right, so we can begin to start talking about our subsystems in a little more detail, starting with the lifting solution, as you can see right here. So we can begin to just briefly go over the requirements we have for this system. So basically, server racks can vary in height. Generally, they can end up being pretty tall though. So this can make it particularly difficult for AWS maintenance workers to get a server that may be faulty, that may be all the way on the top of this rack. So we want to be able to come up with a mechanical solution to help make this process a little more efficient. And that way we could create some mechanical solution to raise sensors to collect data for these AWS maintenance workers. Additionally, we need to design for a 7.5 feet tall server rack. However, we need to consider that whatever solution we came up with had to be able to decrease in size as well, just considering that doors oftentimes are 6.5 feet tall, and there obviously will be many of those throughout the data center. So here we have a little diagram just demonstrating how it would be moving. We ended up going with linear actuators as the mechanism we want to implement in this system. So linear actuators are particularly useful in applications that have accuracy and repeatability as really important factors. So just through research and consideration of our options, we ended up going that route. Additionally, we have a sensor platform here, and that will have a thermal imager as well as a microphone, and that will be able to collect data throughout the full height of the server rack. So here you can see in a little more detail, we have an upper actuator and a lower actuator. The lower actuator will be mounted to the cart. Additionally, you can see there on the middle, we have a piece that's labeled as the aluminum C channel. And what that is basically a mounting system that we're using and we help design to ensure that we're able to piece these two actuators stably together, just so that when it's fully extended to that 7.5 feet height, we don't have any worries about any issues with this system. And here you can see that system in a little more detail. We have the bracket right there that I mentioned earlier. That long piece is the aluminum C channel, and we attached various aluminum and stainless steel brackets that we helped make ourselves just to ensure that we had as many connection points as possible to piece these two actuators together. And again, we can see that little video of the system working again. I just want to mention right here that this is a lot faster than the actual time it will take for it to fully span the height of the server rack. The height we actually ended up reaching was 60 seconds for the travel time of the full 7.5 feet. And that's without any stops for data collection, which will have to be done if used in an actual data center. And lastly, I just want to quickly mention that, again, as mentioned in their presentation, the electrical and computer engineering team were the ones that helped design the control system for our lifting mechanism.
So now we'll be moving into talking about the design of our cart frame itself. So it's just to go into some of the requirements for a cart frame, the big constraint is that we want to have it be easily used by the operator. This operator may be pushing this cart around for 8 hours a day collecting data, and we want it to be a semi-pleasant experience for them. The cart has to also house all of the sensors and electrical components of the cart and within the frame of the cart. And we want the cart to be easily assembled and disassembled in the case that it has to be transported between multiple data centers. So for the material of our cart, we chose to move forward with aluminum T-slot extrusion in order to have the strength for the cart that we required, while also keeping it relatively light and modular. And you may be wondering why we want our design to be modular. Because this project is an iterative project, we wanted to leave the design modular so that it can be adjusted as the user base may need or for future designs. The dimensions of the cart are 20 inches wide by 39 inches long by 76.5 inches tall, which is just under 6.5 feet. So it will be able to travel through doorways with ease. And the width constraint of 20 inches was designed so that it could easily travel through the data center racks, which we were given as a width of 34 inches as our working space, along with being able to travel through doorways, which are about 24 inches wide. The handles for the cart are also located about 40 inches off the ground, which is about 3.5 feet, which is about a relatively normal height for our carts. And then with the cart, it had 4 primary platforms for the mounting of electrical components. The first platform is our operations platform, which is where the laptop and the joystick for the actuators will be mounted. The next platform is our battery and power supply platform, which is located at the base where all of the housing for the power is being located. We then have the environmental sensors, which would be located on the front of the cart. And then on the front in the bottom, we will have the network hub. So as they mentioned, like the Ethernet ports and the Raspberry Pis will be all located on that platform. And then the final aspect of our cart that we want to discuss is that it was designed to interface with our lifting mechanism. Some main issues that occurred with the lifting mechanism is that it had to reach 3 inches off the ground, which meant that either we had to put the base of our cart 3 inches off the ground, or we had to provide a method for it to travel through the base of the cart, which we implemented with this gap in the frame. And then we also implemented a vertical support for the actuators so that there's no risk of them tipping over through their use.
So next we're going to talk about our sensor integration and how we integrated all these electrical and computer components into our cart. So we're going to have 2 main ways of doing this, a quick connect and connect system and a more permanent system. This will make sure all of our sensors are secured to our cart and will be easy to use for our operator. For our quick connect, there's no tools required, and this will all increase the efficiency for the operator. So for our quick connect, we're going to use this CamVate quick release plate. We're going to use this on all our expensive sensors, such as our thermal imager. It has standardized threading, so you can use it on different sensors in the future, and it operates by a quick twist of the red knob right there. For our permanent sensor mounts, they're 3D printed with plastic. You just put the sensor on there and screw it on, and it'll stay on there for the life of the cart. Next is our barcode reader arm. It's our only manual operation on the cart. It'll be on the back operator end on the right and left side. It has a custom 3D printed housing for the barcode reader so it can read barcodes on the floor. It uses this T-slot locking pivot to pivot in a small extension so that it can read the barcodes on the floor. So here's our full design, our lifting system, along with our cart frame and all our sensor integration. So our main takeaways is that design is an iterative process. We are the 2nd iteration of this, and we hope there are many more, but also iterations within the design process that we've gone through. Our cart started off as a block, and it turned into what you see today. We also want to set up future student groups really well by providing them tons of documentation, SolidWorks models, and all our calculations that go along with it, in the hopes that they can achieve full autonomy in the future. So for some of these recommendations, we recommend putting these Swerve MK4 wheels on. It was an idea brought up, but due to time constraints, we couldn't do it. Optimizing the actuator system. Right now it's a little bulky and it sticks out of our car frame just a little bit, the sensor platform. So optimizing that and making sure everything's within the cart frame itself. Improve cable management. This is kind of a big one that we put off until the end. Right now, it's just cable sheets and clips right now to kind of keep it all together, which it does well, keeping it along the T-slot, but using something like this cable drag system for the moving parts on the linear actuator. And then, like I said earlier, the barcode arm is the only manual operation. So really automizing that process will help future iterations. Thank you.
I was wondering, why is there housings around all the sensors? I know you printed a lot of housings for all the different sensors. I was wondering why that was a design decision.
The main use that we had for the sensor housings was just to, in the case that some object was able to go through the frame of the cart, it would cause damage to the sensor housing, and the sensor housing could absorb most of the impact so that we can potentially reprint a housing instead of having to buy another camera or buy another sensor that got damaged.
Other questions?
What was the bill of material cost for the cart and all the sensor hardware?
So the cart itself added up to about $3,000, and I believe with the sensors being around $4,000, higher than $4,000, it'll probably be around $10,000 as it stands right now.
This is probably a question that both teams would have to answer, but during testing, did you guys ever determine how long it takes to scan an entire server rack?
From our testing, we were unable to figure that out. We had a little bit of issues on our testing day with running our programs and just having hardware issues in general. So we were not able to actually test how long it took to collect data for the whole server rack.
This is probably a better question for both teams, but as I was actually on the design team last year, I know you changed the visual cameras to a barcode, and I was wondering why you didn't implement a linear actuator for the barcodes as well, because it made sense, or attach the, because from my understanding from your presentation is that the IR cameras, the thermal cameras, are the ones moving up and down, but the barcode is manual.
So for our implementation, we were told to work with, so I know for last year's cart, it was to scan each individual barcode on each server rack. For this year's iteration, we kind of took a step back and we were told that there was a barcode that was established for each server rack itself that would be located on the floor. So our goal was just to scan that barcode and then collect data for the whole server rack as a whole, with the idea that the maintenance worker could then know a server rack to go look and establish if it's functioning or not.
Thank you. Any other questions for the team? All right, let's thank the team. And if you do have questions for any of the teams that presented today, please visit them at their posters during the poster session, which begins now at 4:15. Thank you all for attending.